A teaspoon of matter weighs 6 billion tons. That is not a metaphor. That is not science fiction. That is the actual measured density of a neutron star, and it is sitting out there right now, scattered across our galaxy in the corpses of dead suns. These objects should not be possible. They violate every instinct you have about how matter behaves, how gravity works, how anything in the universe is allowed to exist. And yet there are millions of them, spinning in the dark, some of them beaming radiation directly at Earth with a precision that makes atomic clocks look sloppy. We have been studying neutron stars for more than half a century. We have built entire observatories to listen to their pulses. We have detected the gravitational waves they release when they collide. We have measured their mass, their spin, their magnetic fields, and the more we learn, the less sense they make. There are neutron stars out there sending us radio signals that repeat every 22 minutes, a rhythm no known physics can explain. There is one called Geminga, 800 light-years away, quietly pelting our planet with antimatter. There are explosions tied to these objects that burn 200 million times brighter than the sun and last for 100 days, and no one can tell you what is actually happening inside them. This is not a story about distant abstract objects that have nothing to do with us. This is a story about the universe operating at the absolute edge of what matter and space-time can survive. About signals arriving at Earth right now from objects whose interiors may contain states of matter that do not exist anywhere else in the cosmos. About the fact that we live in a galaxy filled with things whose cores are so extreme, we are still guessing at what they are made of. This is that story. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From stellar ruin to galactic listening posts, we will follow clues toward the frontier of understanding, and at every turn darkness will answer with a signal, precise, violent, and not yet understood. A star dies in silence. Well, technically it dies in the loudest explosion the universe has to offer, but out there, 10,000 light-years away, through the vacuum where sound has no business travelling, the death happens without a whisper reaching your ears. What does reach us, eventually, is light, and if you happen to be watching the right patch of sky at the right moment with the right instruments, you would see a star that had been sitting quietly in the darkness suddenly outshine its entire galaxy. For a few weeks, maybe a month, that single dying star would pump out more light than 100 billion suns, then it would fade, and what would be left, assuming the universe's math worked out in a very specific way, would be an object so dense, so wrong by every intuitive measure of how matter should behave, that the first scientists to predict its existence didn't really believe it could be real. They published the theory anyway. Turns out they were right. This is where neutron stars come from. Not from nothing, not from some exotic cosmic accident, but from the ruins of something that used to be ordinary, a star. The kind of object we have spent centuries romanticizing, navigating by, writing poetry about. Except this particular kind of star was massive, and when a massive star runs out of options, the universe does not offer it a dignified retirement. It offers it collapse, fire, and in the rarest cases resurrection as something that should not exist. Let's rewind. Long before there is a neutron star, there is a cloud, a nebula, hundreds of light-years across, mostly hydrogen, some helium, traces of heavier elements left behind by previous generations of stars that lived, died, and scattered their guts into the interstellar medium. The cloud is cold, just a few dozen degrees above absolute zero, and it is mostly empty, but not entirely. Pockets of the cloud are slightly denser than others. Gravity, which is patient and has no competing hobbies, begins to pull those dense pockets inward, slowly at first, then faster. As the cloud contracts, it heats up. Basic physics. Compress a gas and it warms. The centre of the collapsing region gets hotter and hotter, and the pressure starts to climb. For a while, nothing dramatic happens. The cloud just keeps falling inward, heating up, glowing faintly in infrared. Then, if the collapsing core gets dense enough and hot enough, something extraordinary occurs. Hydrogen nuclei, which have been bouncing off each other for millions of years, finally collide with enough energy to overcome the electromagnetic repulsion that normally keeps them apart. They fuse. 2 hydrogen nuclei become 1 helium nucleus. In the process, a tiny amount of mass converts directly into energy. That energy, in the form of heat and light and pressure, pushes outward against the inward crush of gravity. For the first time in its existence, the protostar stops collapsing. A star is born. And that balance, that razor-thin equilibrium between the inward pull of gravity and the outward push of fusion-generated pressure, is what defines a living star. Our Sun has been running that balance for about 4.5 billion years. It will keep running it for another 5 billion or so. The Sun is ordinary. It sits comfortably on what astronomers call the main sequence, a long stable phase of stellar life where fusion hums along at a steady rate, gravity stays satisfied, and nothing explodes. A star like our Sun will eventually swell into a red giant, puff off its outer layers, and leave behind a white dwarf. A dense, hot ember about the size of Earth, supported not by fusion but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. White dwarfs cool slowly over trillions of years. They do not explode. They do not collapse further. They just sit there fading. Now scale everything up. Take a star not 1 solar mass but 8, 10, 20, 50. Massive stars live fast. They burn through their hydrogen in a few million years instead of billions. When the hydrogen in the core runs out, the core contracts and heats up until it's hot enough to fuse helium into carbon, then carbon into oxygen, oxygen into neon, neon into magnesium. The star builds a layered structure like an onion, each shell fusing lighter elements into heavier ones, each new stage of fusion requiring higher temperatures and pressures than the last, and each stage runs faster than the one before it. A massive star might spend 1 million years fusing hydrogen, a few 100,000 years fusing helium, a few 100 years fusing carbon, a few months fusing oxygen. And when it reaches silicon fusion, the final stage before iron, the clock runs out in a matter of days. Iron is the wall. Fusing elements lighter than iron releases energy. Fusing iron costs energy. Once the core of a massive star starts producing iron, fusion stops being a solution to the gravity problem. The core, now made of iron nuclei packed together at unimaginable density and temperature, has nothing left to burn. For a brief moment, the core just sits there, inert, a ball of iron roughly the size of Earth, weighing about 1.5 times the mass of our Sun, held up by electron degeneracy pressure, the same quantum effect that keeps white dwarfs stable. Except this core is hotter, denser, and heavier than any white dwarf ever gets on its own. The pressure is unbearable, and then the core blinks. Electrons, which had been holding the line, get shoved into protons. The electromagnetic repulsion that keeps matter from collapsing past a certain point simply stops mattering. Electrons and protons combine into neutrons. The core loses its pressure support in less than a second, and it falls. Not slowly, not gently. The collapse happens so fast that the outer layers of the star don't even know it started. In about 1/4 of a second, an object the size of a planet compresses down to something the size of a city. The density skyrockets. The temperature climbs past 1 billion degrees, and then the collapse stops. Not because gravity gave up, because the neutrons themselves, packed together at nuclear densities, finally exert enough quantum pressure to halt the inward crush. Neutron degeneracy pressure, the same principle that kept electrons from collapsing further, now operating 1 level deeper in the particle hierarchy. The rebound is violent. The infalling outer layers of the star, which had been racing toward the core at a significant fraction of the speed of light, slam into the newly formed neutron core and bounce. The shockwave rips outward through the star at thousands of kilometers per second, tearing it apart from the inside. The outer layers, still rich in hydrogen and helium, explode into space. For a few weeks, the dying star becomes one of the brightest objects in the sky. We call this a Type II supernova. And what it leaves behind, if the core mass falls within a very specific range, is a neutron star. Let's pause there because the terminology matters and it trips people up constantly. Not all supernovae make neutron stars. Type E supernovae, specifically Type Ia, come from white dwarfs that have been fed too much mass by a companion star. The white dwarf hits a critical threshold called the Chandrasekhar limit, about 1.4 solar masses, and it detonates in a runaway thermonuclear explosion. The entire white dwarf is destroyed, no remnant, no neutron star. Useful for measuring cosmic distances because the explosions are remarkably consistent in brightness, but irrelevant to this story. Type 2 supernovae are different. These are core collapse events. The explosions we just described. Massive stars running out of fuel, collapsing, rebounding, and leaving something behind. That something, if conditions are right, is a neutron star. If conditions are slightly wrong, it's a black hole. The dividing line sits somewhere around 2 to 3 solar masses for the remnant core. Below that, neutron degeneracy pressure wins. You get a neutron star. Above that, even neutrons can't hold the line. Gravity wins. The core collapses past the point of no return and you get a black hole instead. The exact threshold is still debated. It depends on the equation of state for nuclear matter, a topic physicists argue about with the kind of intensity usually reserved for sports rivalries. But the basic picture holds. Small remnant core, white dwarf, medium remnant core, neutron star, large remnant core, black hole. So a neutron star is what you get when a massive star dies, but not too massive. When the core collapses, but not all the way. When the universe decides to stop the collapse at exactly the moment matter reaches the density of an atomic nucleus, and then just leaves it there, frozen at the edge of becoming something even stranger. Neutron stars were predicted in 1934 by two astronomers, Walter Baird and Fritz Zwicky, only a year after the neutron itself was discovered. They were trying to explain supernovae, which at the time were barely understood, and they suggested that the collapse of a massive star's core could compress it into a ball of neutrons. The idea was wild. The density required was absurd. Most of the astronomical community ignored it. Some thought it was interesting in a theoretical sense, but probably not real. Building a star out of neutrons seemed like the kind of thing you could write equations about, but never actually find in nature. Then in 1967, a graduate student named Jocelyn Bell Burnell was analysing radio data from a new telescope in Cambridge when she noticed something strange. A repeating signal, a pulse, every 1.3 seconds like clockwork. She and her advisor, Anthony Hewish, checked for interference. They checked for satellites. They jokingly considered aliens. The signal kept pulsing. It wasn't random noise and it wasn't a mistake. It was real. And it was coming from space. They called it a pulsar. Within months, more were found. All of them pulsing at regular intervals, some faster than once per second. The only object that could spin that fast without flying apart was something extraordinarily small and extraordinarily dense. A white dwarf was too big. A normal star was out of the question. The only thing that fit the data was a neutron star. Suddenly, Baird and Zwicky's wild idea from 1934 wasn't theoretical anymore. It was sitting in the data, ticking away like a cosmic metronome. Pulsars are neutron stars. Specifically, they're neutron stars that are spinning and beaming radiation out from their magnetic poles. If one of those beams sweeps across Earth, we see a pulse. A lighthouse in space, except the lighthouse is the size of Manhattan and spinning hundreds of times per second. We'll come back to pulsars in a later chapter. For now, what matters is that their discovery confirmed neutron stars were real. Not just mathematically possible, real. And once astronomers knew what to look for, they started finding them everywhere. In supernova remnants, in binary systems with other stars, orbiting each other in pairs. Today, we've catalogued thousands of neutron stars. Some are quiet, some scream across the electromagnetic spectrum, some have magnetic fields so strong they warp the very atoms in their atmospheres, and every single one of them started the same way. A massive star ran out of fuel. Its core collapsed. The outer layers exploded, and what remained was an object about 20 kilometers across, weighing more than our sun, spinning faster than a helicopter rotor, and dense enough that a single teaspoon of its material would weigh more than every human being on Earth combined. Actually, depending on which estimate you trust, a teaspoon would weigh somewhere between 10 million tons and 1 billion tons. The range is absurd. The uncertainty comes from the fact that we still don't fully understand the equation of state for matter at those densities. We can model it, we can constrain it with observations, but the interior of a neutron star is operating in a regime of physics we cannot replicate in any laboratory on Earth. We are guessing, educated guessing, but guessing nonetheless. What we do know is that the density is somewhere in the neighbourhood of 3.7 times 10 to the 17th kilograms per cubic meter in the outer layers, and possibly as high as 8 times 10 to the 17th deeper inside. For reference, Water has a density of 1,000 kilograms per cubic meter. Lead is about 11,000. The core of the Earth peaks at around 13,000. A white dwarf clocks in at roughly 10 to the 9th. A neutron star is 10 to the 14th times denser than water. It is approximately the same density as an atomic nucleus. If you could somehow scoop up all the neutrons in every atom in your body and compress them into a single point with no empty space between them, you would have neutron star matter. Except you can't. Because outside the core of a collapsing star, there is no force in the universe strong enough to compress matter to that degree. Gravity is the only tool capable of building a neutron star, and it only gets one chance. The collapse happens once. If the core overshoots the neutron star threshold, it keeps falling and becomes a black hole. If it undershoots, it never compresses far enough and you get a white dwarf instead. The window is narrow, the process is violent, and the result is an object that sits at the absolute edge of what the universe allows matter to be before it stops being matter and becomes something else. This is the cosmic graveyard. Not a quiet place where stars go to fade, a forge, a recycling centre, a place where the heaviest elements in the universe are born in the blast, scattered into space, and eventually incorporated into the next generation of stars and planets. Every atom of carbon, oxygen, iron and gold in your body was created inside a star. A significant fraction of those atoms were created in the supernova explosions that either formed neutron stars or tried to. You're made of stardust, but more specifically you are made of the shrapnel from stellar catastrophes. When a massive star dies, it does not just create a neutron star, it seeds the surrounding interstellar medium with heavy elements. Those elements drift, mix with hydrogen clouds, and eventually collapse into new stars. Some of those stars have planets, some of those planets have the right conditions for chemistry, and billions of years later, someone standing on one of those planets points a telescope at the sky and detects a faint repeating pulse from an object 20,000 light-years away, an object that used to be a star. And they realize, slowly, uncomfortably, that the atoms in their hand and the atoms in that neutron star were born in the same kind of fire. So when we talk about neutron stars as remnants, we are not talking about leftovers in the sense of something useless. We're talking about the compressed hearts of dead giants, objects that contain more mass than our sun, spin faster than any object we can build, generate magnetic fields trillions of times stronger than anything on Earth, and sit quietly in the darkness, ticking. They are not asteroids. They are not planets. They are not normal stars. They are something else entirely, a state of matter that only exists because gravity, given the right starting conditions, can crush a stellar core past every threshold we thought was final until the neutrons themselves say stop. And even then, the universe is not quite finished with them. Because neutron stars do not just sit there. They spin. They radiate. They orbit each other in binary systems spiraling inward over millions of years, losing energy to gravitational waves, until eventually they collide in explosions so violent they forge elements heavier than iron. Elements like platinum and gold. We have detected those collisions. We have measured the ripples they send through space-time, and what we are learning slowly is that neutron stars are not just the remnants of stellar death. They are engines, factories, laboratories where the universe experiments with physics at its breaking point. But before we get to what neutron stars do, we need to understand what they are made of, and that is where things get truly strange. So you've watched a star die. You've seen the core collapse, the outer layers explode, and what remains is an object the size of a city containing more mass than the sun. We called it a neutron star and moved on as if giving it a name somehow made it less absurd. It doesn't, because now we have to talk about what that object actually is, not what it's called, what it is. And the answer is going to sound like science fiction until you realize it's just physics taken to an endpoint most people never think about. Let's start with a number, 10 quadrillion kilograms per cubic centimetre. That's the density we're dealing with in the title of this video, and it's a real estimate for the deeper layers of a neutron star. Not a metaphor, not an exaggeration, an actual measurement derived from observations of how these objects behave when we watch them spin, orbit, and occasionally collide with each other. To put that in perspective, a cubic centimetre is about the size of a sugar cube. On Earth, a sugar cube full of water weighs 1 gram. A sugar cube full of lead weighs about 11 grams. A sugar cube full of the densest material we can create in a laboratory, osmium, weighs about 22 grams. A sugar cube full of white dwarf material, the kind of dense stellar remnant we mentioned earlier, would weigh somewhere around 1 ton. A sugar cube full of neutron star material from the outer layers would weigh about 1 billion tons. And if you somehow scooped up a sugar cube's worth of matter from the core, the number climbs even higher. 10 billion tons, maybe more. We're not entirely sure because the physics at that density stops being something we can test in a lab and starts being something we can only model with equations that may or may not be right. Here's the thing that breaks most people's intuition. Density is not just about how much stuff you cram into a space, it's about how that stuff is arranged. Normal matter, the kind you interact with every day, is mostly empty. Your body's made of atoms. Atoms are made of nuclei surrounded by clouds of electrons. The nucleus is tiny, about 100,000th the diameter of the atom itself. The rest is empty space. If you could strip away all that empty space and crush the nuclei and electrons together with no gaps, your body would fit into a cube smaller than a grain of sand. And it would weigh exactly the same. You wouldn't have lost any mass. You would have just removed the illusion of solidity. A neutron star is what happens when gravity removes that illusion on a cosmic scale. It doesn't just crush matter, it changes the rules for how matter is allowed to exist. To understand that, you need to understand the forces holding normal matter together in the first place, and that means we have to talk about pressure. Not the kind of pressure you feel when someone squeezes your hand. Quantum pressure. The kind that comes from the fact that particles at the smallest scales don't like being in the same place at the same time. In normal matter, electrons are the first line of defense. They orbit atomic nuclei in clouds defined by quantum mechanics, and one of the ironclad rules of quantum mechanics is the Pauli exclusion principle. It says that no two fermions, particles like electrons, can occupy the exact same quantum state at the same time. You can't put two electrons in the same place with the same energy and the same spin. If you try to squeeze them together, they push back, not because they're physically bouncing off each other, but because the mathematics of quantum mechanics forbids the overlap. That resistance is called electron degeneracy pressure, and it's what keeps white dwarfs from collapsing. A white dwarf is what you get when a star like our Sun dies, and leaves behind a core made mostly of carbon and oxygen. No more fusion, no more heat. Just a ball of nuclei sitting in a sea of electrons. The electrons packed together at high density exert degeneracy pressure. That pressure doesn't depend on temperature. It depends purely on how tightly the electrons are confined. The smaller the space, the higher the pressure. In a white dwarf, that pressure is enough to hold up about 1.4 solar masses in an object roughly the size of Earth. Push the mass higher, and the electrons can't hold the line anymore. They get forced into the nuclei. Specifically, they get forced into protons. An electron and a proton combine to form a neutron and a neutrino. The neutrino escapes, the neutron stays, and suddenly the star has lost the pressure support that was keeping it stable. This process is called neutronization, and it's the key to why neutron stars exist at all. Electrons don't just disappear, they get converted, and when that happens, the rules change. You're no longer dealing with a gas of electrons providing pressure, you're dealing with neutrons, which are also fermions, which means they also obey the Pauli exclusion principle. Neutron degeneracy pressure. It works the same way electron degeneracy pressure does, but it kicks in at much higher densities because neutrons are about 2,000 times heavier than electrons. Heavier particles require more extreme conditions to generate the same quantum resistance. In a collapsing stellar core, once the density climbs past a certain threshold, the electrons lose and the neutrons take over. The core stops collapsing when neutron degeneracy pressure finally balances gravity. That balance point is a neutron star. Now let's talk about what that actually looks like inside. Because calling it a ball of neutrons is accurate in the same way calling a car a metal box with wheels is accurate. Technically true, deeply misleading. A neutron star has layers, structure, phases of matter that transition from something almost normal at the surface to something we can't even name with confidence at the center. And every layer is stranger than the one above it. The outermost layer is called the atmosphere, but we'll save that for the next chapter. Just below that is the crust. The crust of a neutron star is not rock. It's not like Earth's crust. It's a solid lattice of atomic nuclei, but the nuclei are not the familiar ones you learned about in chemistry class. These are neutron-rich isotopes, nuclei with far more neutrons than protons, squeezed together at densities where normal atoms can't exist. The electrons have been stripped away, not converted yet, just ionized and floating freely. The nuclei sit in a rigid lattice, vibrating slightly, held in place by the electromagnetic forces between them. The density at the top of the crust is around 1 billion kilograms per cubic meter. That's already 1,000,000 times denser than anything on Earth, and it gets worse as you go deeper. As you descend through the crust, the pressure climbs. The nuclei get heavier, more neutron-rich, more distorted. At a certain depth, the density hits a threshold called the neutron drip point. This happens at around 2 to 4 times 10 to the 11th grams per cubic centimeter, and it's exactly what it sounds like. The nuclei become so overloaded with neutrons that they can't hold them all anymore. Neutrons start leaking out, dripping into the space between nuclei, forming a gas of free neutrons mixed with the lattice. The nuclei are still there, still forming a solid structure, but now they're sitting in a sea of unbound neutrons. The deeper you go, the more neutrons leak out, and the denser that neutron sea becomes. By the time you reach the bottom of the crust, the density is around 10 to the 14th grams per cubic centimeter. The lattice of nuclei is barely holding together. The neutron gas is almost as dense as the nuclei themselves, and then the crust ends. What comes next is called the outer core, and this is where things get truly strange. The nuclei dissolve, they don't explode, they don't break apart in any violent sense, they just stop being separate objects. The density is so high that the boundaries between nuclei become meaningless. What you're left with is a nearly uniform fluid of neutrons, with a small fraction of protons and electrons mixed in. The protons and electrons are still there because you can't convert absolutely everything. Some protons remain, and they carry electric charge, which means they interact with the neutrons in complicated ways. The mixture behaves like a superfluid, a quantum fluid with zero viscosity. If you could somehow stir it, it would keep swirling forever. There would be no friction to slow it down. The superfluid behavior is not a guess. We have indirect evidence for it from observations of pulsars. Pulsars are spinning neutron stars, and some of them occasionally glitch. They suddenly spin faster for a brief moment, then gradually slow back down. The explanation, according to current models, is that the superfluid interior and the solid crust are rotating at slightly different speeds. Most of the time, they're locked together by magnetic forces and friction, but occasionally the superfluid builds up angular momentum and suddenly transfers some of it to the crust. The crust spins up. A glitch. The fact that this happens at all tells us the interior is not a normal fluid. Normal fluids don't store angular momentum the way superfluids do. This is real physics confirmed by observation, and it's happening inside every neutron star we've ever detected. Now go deeper, into the inner core, and this is where the certainty ends and the speculation begins. Because we don't know what's in there. Not for sure. We have models, we have educated guesses, but the density in the inner core is so high, and the pressure so extreme, that the equations we use to describe nuclear matter start giving different answers depending on which assumptions you make. This is the equation of state problem, and it's one of the biggest open questions in astrophysics. The equation of state describes how matter behaves under pressure, how much it resists compression, how its density and pressure relate to each other. For normal matter, we know the equation of state very well. For white dwarf matter, we know it pretty well. For neutron star matter, especially in the core, we're guessing. Here's what we think might be happening. At low densities, matter is made of protons, neutrons, and electrons. At higher densities, neutrons dominate. At even higher densities, the neutrons themselves might start breaking apart. Neutrons are not fundamental particles. They're made of quarks, 3 quarks per neutron, held together by the strong nuclear force. Under normal conditions, quarks are confined. You can't pull a quark out of a neutron and hold it by itself. The strong force doesn't allow it. But at the densities inside a neutron star core, it's possible that the quarks become deconfined. The boundaries between neutrons dissolve, and what you're left with is a soup of free quarks. Quark matter. Some models suggest the core of the most massive neutron stars might contain a quark core, a region where neutrons no longer exist as individual particles, and the matter behaves like a liquid of quarks sloshing around in a space the size of a city block. We don't know if that's real. We have no way to test it directly. The only place in the universe where quark matter might exist in stable form is inside neutron stars. Particle accelerators on Earth can create quark-gluon plasma for fractions of a second by smashing heavy nuclei together at high speeds. but that plasma exists at extremely high temperatures and low densities compared to a neutron star core. It's not the same thing. The quark matter we're talking about here, if it exists, would be cold, or at least cold by nuclear standards, a few billion degrees instead of trillions, and it would be stable, not expanding, not flying apart, just sitting there under the crushing weight of a solar mass worth of neutrons pressing down from above. There's another possibility. Instead of quark matter, the core might contain hyperons. Hyperons are particles similar to protons and neutrons, but they contain strange quarks. Protons and neutrons are made of up and down quarks. Hyperons swap one or more of those for a strange quark, and that changes their properties. Strange matter, as it's sometimes called, would be denser and more exotic than normal neutron matter. Some models predict that at high enough densities, it becomes energetically favourable for neutrons to convert into hyperons. If that's true, the core of a neutron star might be a mixture of neutrons, protons, hyperons, and possibly other strange particles we haven't even thought to look for yet. The trouble is, we can't see inside. We can measure the mass of a neutron star by watching how it affects the orbit of a companion star in a binary system. We can measure its radius, sort of, by analysing the X-rays emitted from hotspots on its surface. We can detect gravitational waves from neutron star mergers and use the signal to infer properties of the matter involved. But we can't crack one open and look inside. Every piece of information we have is indirect. A shadow cast on the data by an object we can never touch. And the uncertainty matters because the equation of state determines everything else. How massive a neutron star can get before collapsing into a black hole, how large it can be, how it behaves when it spins, how it responds to tidal forces during a merger. Get the equation of state wrong, and every prediction downstream is wrong too. Different research teams favour different models, and the debates get heated, not because anyone is being unreasonable, but because the stakes are high and the data is limited. You're trying to reverse engineer the behaviour of matter at densities we can't reproduce on Earth using observations of objects thousands of light years away that we can barely resolve as points of light. Let's ground this in something concrete. The pressure at the centre of a neutron star is estimated at around 1.6 times 10 to the 34th pascals. A pascal is a unit of pressure. 1 pascal is about the pressure exerted by a dollar bill resting flat on a table. Atmospheric pressure at sea level on Earth is about 100,000 pascals. The pressure inside the Earth's core is around 360 billion pascals. The pressure at the centre of a neutron star is 10 to the 34th. You would need a stack of dollar bills stretching across the entire observable universe, repeated trillions of times, to generate that kind of pressure. And that pressure is what's keeping the neutrons from collapsing further. It's a standoff between gravity trying to crush everything into a single point and quantum mechanics saying no, you can't put all the neutrons in the same state. One side is trying to compress the star out of existence. The other side is the fundamental laws of physics, and the result is an object balanced on a knife edge. If you add more mass to a neutron star, the core gets denser, the pressure climbs. At some point, around 2 to 3 solar masses depending on whose equation of state you trust, neutron degeneracy pressure isn't enough anymore. Nothing is enough. The star collapses past the point where even quantum mechanics can hold it up, and it becomes a black hole. The exact threshold is still debated, and one of the major goals of neutron star research is to pin that number down with higher confidence. Because that number tells us something fundamental about the universe. It tells us the maximum density that matter can have before it stops being matter. We've never seen a neutron star above 5 solar masses. We've never seen one that violates the rough upper limit of 3 or so solar masses for stable neutron stars. Either they don't exist or they collapse immediately into black holes. Either way, there's a line. Cross it, and the neutron star ceases to exist. It's replaced by an event horizon, a one-way door where even light can't escape. Neutron stars sit just this side of that line, and they sit there because the universe has rules about how tightly you can pack matter before the rules themselves change. There's a concept in physics called the Tolman-Oppenheimer-Volkoff limit. It's the neutron star equivalent of the Chandrasekhar limit for white dwarfs. The Chandrasekhar limit says you can't have a stable white dwarf heavier than about 1.4 solar masses. Add more mass, and electron degeneracy pressure fails. The TOV limit says you can't have a stable neutron star heavier than some value, probably between 2 and 3 solar masses, depending on the equation of state. Add more mass, and neutron degeneracy pressure fails. Both limits come from the same underlying principle. Quantum mechanics can only provide so much pressure. Push hard enough, and even quantum mechanics loses. The uncertainty in the TOV limit is frustrating because we have candidates, objects that might be right at the boundary. In 2019, the LIGO and Virgo gravitational wave detectors picked up a signal from the merger of two compact objects. One was definitely a black hole, weighing about 9 solar masses. The other was lighter, about 2.6 solar masses, right in the grey zone. Too heavy to be a normal neutron star according to some models, light enough to be a neutron star according to others. We don't know what it was. A very heavy neutron star on the verge of collapse, a very light black hole, something in between, if such a thing can even exist. The signal cut off when the objects merged, and whatever they became afterward is almost certainly a black hole now. But for a brief moment we might have detected an object sitting exactly at the edge of what the universe allows. There's another twist. Neutron stars spin. Some of them spin fast. The fastest known pulsar, designated PSR, J 1748-2446 AD, rotates 716 times per second. That's not a typo. 716 rotations per second. The equator of that neutron star is moving at roughly a quarter of the speed of light. At that rotation rate, the centrifugal force is enormous. The star is trying to fly apart. The only reason it doesn't is because gravity and the structural integrity of neutron-rich matter are just barely strong enough to hold it together. If you spun it any faster, the surface would start to shed material. There's a speed limit, and some neutron stars are brushing up against it. The combination of extreme density and extreme rotation does something strange to space-time itself. Einstein's general relativity tells us that mass and energy curve space-time, and rotation drags space-time along with it. Near a spinning neutron star, space itself is being twisted. If you tried to hover in place near the surface, you would find yourself being dragged along in the direction of the star's rotation, not because of air resistance or friction, because space itself is rotating. The effect is called frame dragging, and it's been measured around Earth using satellites. Earth's frame dragging effect is tiny. A neutron star's is not. Close to the surface, the frame dragging is so strong that it would be nearly impossible to orbit in the opposite direction of the star's spin. Space wouldn't let you. And we haven't even talked about the magnetic fields yet. Some neutron stars have magnetic fields 1 trillion times stronger than Earth's. At those field strengths, the magnetic field affects the behavior of atoms, distorts the shape of molecules, and can pull iron out of the star's surface and suspend it in the magnetosphere. The field is strong enough that it affects the vacuum itself, creating virtual particle pairs that flicker into existence and change the way light propagates. These objects are called magnetars, and they're an entire category of strangeness we'll return to later. The point is, neutron stars are not simple. They are not just dense, they are laboratories where every extreme we can imagine is happening at once. Density 10 to the 14th times higher than water. Pressure 10 to the 34th pascals. Rotation speeds 1/4 of the speed of light. Magnetic fields strong enough to bend space-time. Superfluidity in the core. Possibly quark matter. Possibly hyperons. Possibly something we haven't thought of yet. And all of it held together by a balance between gravity and quantum mechanics that sits within a few % of total collapse. When physicists talk about the interior of a neutron star, they're not guessing wildly. They're working from the best models we have, constrained by every observation we can make. But the honest ones will tell you there's still a lot we don't know. We don't know the exact composition of the core. We don't know whether quark matter exists in nature. We don't know the precise equation of state. We don't know the upper mass limit with certainty. We know these objects exist. We know roughly how they behave. But the fine details, the stuff that would let us say definitively what's inside, are still out of reach. And that uncertainty is not a failure, it's a frontier. Every new observation, every new neutron star binary, every gravitational wave detection gives us another data point, another constraint on the models. Slowly we're closing in on the truth. In the last few years, observations of neutron star mergers have started to narrow the range of possible equations of state. The way the stars deformed during the final moments before collision tells us how stiff or soft the matter is, how much it resists compression. Those measurements are starting to rule out some of the more extreme models. We're not there yet, but we're getting closer. So when someone tells you a neutron star is dense, they're not just talking about weight. They're talking about a state of matter that but only exists because the universe allows one very specific loophole. If gravity is strong enough, and the mass is in the right range, quantum mechanics will resist collapse just long enough to create something stable. Too light, and you get a white dwarf. Too heavy, and you get a black hole. But in that narrow window, you get an object where the density is so high that atoms dissolve, nuclei merge, and matter itself changes phase into something we can barely describe. And all of it fits inside a sphere 20 kilometers across. You could drive across a neutron star in 15 minutes if there were roads, and if the gravity didn't immediately crush you into a thin layer of atoms smeared across the surface, which it would. Because the surface gravity of a neutron star is about 100 billion times Earth's. Stand on the surface, which you can't, and you would weigh as much as a large mountain. Your body would collapse into a sheet of nuclei a few atoms thick before you had time to process what was happening. The tidal forces alone would rip you apart on the way down, but the neutron star wouldn't care. It would just keep sitting there, spinning, radiating, ticking away like a cosmic clock built from the ruins of a star that used to be ordinary. And somewhere in the core, under pressures we can't replicate and densities we can't fully model, matter is doing something we still don't entirely understand. That's where we are. That's the frontier, and the next step is understanding what happens at the surface. Because as strange as the interior is, the outside is somehow even weirder. We left off standing at the edge of understanding what neutron stars are made of, staring down into a core where matter behaves in ways we can barely model. Now we need to come back up. Because as strange as the interior is, the surface is where the consequences of all that compressed weirdness become visible, or at least as visible as anything can be on an object that sits thousands of light years away and measures 20 kilometers across. So let's talk about the surface of a neutron star. Not metaphorically, not as a thought experiment. Let's talk about what it would actually be like to approach one of these things, what you would see, what you would feel, and how quickly everything would go catastrophically wrong. First, the gravity. We mentioned this briefly in passing, but it deserves more attention because the numbers are not just large. They are violence rendered as physics. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's. That is not a typo, not an exaggeration for effect. 200 billion. If you weigh 70 kilograms on Earth, standing on the surface of a neutron star, assuming you could somehow stand without immediately ceasing to exist as a coherent object, you would weigh roughly 14 billion kilograms, 14 million tons, the weight of a small mountain. Except, you're not a mountain. You are a soft biological structure held together by chemical bonds that were never designed to resist that kind of force. Let's be very clear about what happens next, because popular science tends to gloss over this part, or dress it up in language that makes it sound almost poetic. You do not land on a neutron star. You do not have time to take in the view, or think a final thought or experience anything resembling a prolonged descent. The moment you get close enough for the gravity to matter, you stop being you. Tidal forces rip you apart before you ever touch the surface. Tidal forces are the difference in gravitational pull between one part of your body and another. On Earth, they are negligible. Your head and your feet experience essentially the same gravitational acceleration. Near a neutron star, that is no longer true. If you're falling feet first, your feet are closer to the star than your head. The difference in distance is only about 2 meters, the length of a human body. But the gravitational gradient is so steep that your feet experience significantly more pull than your head. Significantly is underselling it. Your feet would be accelerating toward the surface thousands of times faster than your head. The result is that you get stretched, pulled apart along your length. Astronomers call this spaghettification, and the term is both accurate and horrifying. Long before you reach the surface, your body elongates, bones snap, muscles tear, blood vessels rupture. Your cells are pulled apart at the molecular level, and because the gravity is so strong, this does not happen over minutes or even seconds. It happens in fractions of a second. You would not have time to process pain. You would not have time to process anything. One moment you are a person. The next moment you are a thin stream of dissociated atoms accelerating toward a surface that is already hot enough to vaporize you. But let's say, for the sake of understanding, that we could somehow protect you from the tidal forces. Let's say we wrap you in a magical indestructible shell that holds your body together and shields you from the stretching. You still would not survive. because now we have to talk about what happens when you actually touch the surface. The escape velocity from a neutron star, the speed you would need to leave its surface and reach infinity, is about half the speed of light, roughly 150,000 kilometers per second. If you are falling toward the surface from any significant distance, by the time you hit, you are moving at a substantial fraction of that speed, tens of thousands of kilometers per second at minimum. When you strike the surface at those velocities, the kinetic energy is absurd. You would not bounce. You would not splat. You would convert into a burst of heat and radiation on impact. Every atom in your body would be moving so fast that molecular bonds become irrelevant. You would essentially undergo a very small, very brief fusion event as your nuclei collide with the nuclei in the surface material at relativistic speeds. You would flash into plasma and then into radiation, a brief flicker of light against a background that is already glowing white hot. And if somehow, impossibly, you survive that impact, you would immediately be crushed. Because the gravity is not just strong in the sense that it pulls hard, it is strong in the sense that it compresses. The pressure at the surface of a neutron star is immense. Your body, held together by electromagnetic forces between atoms, would be flattened, compressed into a layer a few atoms thick. You would not be a person anymore. You would be a smear, a thin film of nuclei spread across the surface like paint, and that smear would then begin to sink. Because the surface of a neutron star is not a solid platform in the way we think of solid, it is more like a crust floating on an ocean of neutrons, and anything that lands on it gets pulled down and incorporated into the structure. You would not stay on the surface. You would become part of the crust. Your atoms, now compressed beyond recognition, would join the lattice of neutron-rich nuclei that make up the outer layer. And eventually, if you sank deep enough, even those nuclei would dissolve into the neutron fluid below. So no, you cannot visit the surface of a neutron star. You cannot even get close. The object itself is hostile to the existence of anything resembling normal matter. Standing on it is not an option. Hovering near it is not an option. Even observing it from a few kilometers away would expose you to radiation levels that would sterilize you in seconds and kill you in minutes. Neutron stars emit X-rays, gamma rays, and intense magnetic fields. If the neutron star happens to be a pulsar, which many of them are, you would also be swept by a rotating beam of radiation that could deliver a lethal dose every time it passed over you. Approaching a neutron star is not dangerous in the way that climbing a mountain is dangerous, or flying a plane through a storm is dangerous. It is dangerous in the way that standing next to a nuclear detonation is dangerous. The environment does not give you a chance to react, it simply ends you. Now let's talk about what the surface actually is, because from a safe distance through a telescope it does not look like much. Neutron stars are small, 20 kilometers across. At typical distances of thousands of light years, they are point sources. We cannot resolve surface features the way we can with planets, or even normal stars. What we can do is measure their radiation, analyze the spectrum, and infer properties. And what we have inferred is that the surface of a neutron star is one of the most extreme environments in the universe. The temperature of a neutron star's surface varies depending on its age and activity level. Young neutron stars, freshly formed from supernova explosions, can have surface temperatures above 1 million degrees Celsius. Older ones cool down, but even after millions of years, the surface temperature can still be in the range of a few 100,000 degrees. That is hot enough to emit X-rays. Hot enough that the surface glows blue-white in visible light, though most of the radiation is in higher energy bands. For comparison, the surface of our Sun is about 5,700 degrees Celsius. A neutron star's surface is hundreds of times hotter. And unlike the Sun, where the heat comes from ongoing fusion in the core, the heat on a neutron star's surface comes from leftover thermal energy from the collapse and from friction, as the crust shifts under tidal stresses if the star is in a binary system. The composition of the surface is strange. Normal stars have atmospheres made of hydrogen and helium. Neutron stars do not. Or rather, they do. But the atmosphere is unimaginably thin and made of elements that have been gravitationally stratified. Gravity on a neutron star is so strong that heavier elements sink and lighter elements float. But even the lightest elements are compressed into a layer only a few centimeters thick. The atmosphere, if you can call it that, might be made of hydrogen in some cases, or helium, or even heavier elements like carbon or iron, depending on the history of the star and what material has fallen onto it over time. but this is not an atmosphere in any familiar sense. It is more like a diffuse plasma, a layer of ionized gas held in place by the intense gravity and glowing at temperatures that would vaporize any normal matter. Below the atmosphere is the crust. The crust of a neutron star is a solid, or at least it behaves like a solid in the sense that it can support stresses and fracture under strain. It is made of atomic nuclei arranged in a crystalline lattice, but the nuclei are not the ones you learned about in chemistry. They are exotic, neutron-rich isotopes that do not exist anywhere else in the universe, except possibly in the debris of supernova explosions for a brief moment before they decay. The electrons that would normally orbit these nuclei have been stripped away and are floating freely in a dense electron gas. The nuclei themselves are squeezed together at densities around 1 billion kilograms per cubic meter near the top of the crust. That is already 1 million times denser than the densest material on Earth, and it gets denser as you go deeper. At a certain depth, the density crosses a threshold called the neutron drip point. This is where the nuclei become so overloaded with neutrons that they cannot hold them all. Neutrons begin to leak out, forming a gas that fills the spaces between the lattice of nuclei. Deeper still, the lattice starts to break down. The nuclei deform into shapes that do not exist in normal matter. Long rods, flat sheets, structures that physicists have named nuclear pasta because the shapes resemble spaghetti and lasagna. This is not a joke. The term nuclear pasta is used in peer-reviewed papers because it is the most efficient way to describe what happens when you compress atomic nuclei to the point where they start merging, but have not yet fully dissolved into a uniform fluid. The pasta phase sits at the boundary between the crust and the core, and it is one of the least understood regions of a neutron star because the physics involves both nuclear forces and quantum mechanics, in a regime we cannot test experimentally. The surface itself is not smooth. Models predict that a neutron star's crust can have mountains, not large ones. The gravity is so strong that it crushes any significant deviation from a sphere almost immediately. But small irregularities, hills no more than a few millimeters tall, can exist. A few millimeters does not sound like much, but on an object the size of a neutron star, even that tiny deviation represents an enormous amount of mass in the wrong place. If a neutron star has a mountain a few millimeters tall, the gravitational stress from that asymmetry can cause the crust to fracture. When the crust fractures, it releases energy, a star quake. The crust shifts, the star's magnetic field lines snap and reconfigure, and a burst of radiation is emitted. We have detected these events. In 2004, a neutron star called SGR 1806-20 experienced a starquake so violent that it released more energy in 1/10 of a second than our Sun emits in 100,000 years. The burst of gamma rays temporarily overloaded every detector in the solar system pointed in that direction. That was a millimeter-scale crack in the crust of an object 20 kilometers across. Now let's add rotation, because neutron stars spin. Some of them spin very fast. The fastest known pulsar, PSR J7548, minus 2446 AID, rotates 716 times per second. That is more than 10 times faster than a kitchen blender. And this is an object with more mass than the Sun. When something that massive spins that fast, the centrifugal force at the equator is enormous. The star is trying to fly apart. The only reason it does not is because the gravity and the structural strength of the crust are just barely enough to hold it together. There is a speed limit, a maximum rotation rate, and some neutron stars are close to it. If you spun them any faster, material at the equator would be flung off into space. The rotation also distorts the shape. Neutron stars are not perfect spheres. The centrifugal force from spinning causes the star to bulge slightly at the equator. The distortion is small, only a few % at most, but it is real and it is measurable. When a neutron star is in a binary system and another star is pulling on it with tidal forces, the combination of rotation and tidal distortion can create asymmetries in the mass distribution. Those asymmetries generate gravitational waves, tiny ripples in space-time that propagate outward at the speed of light. The waves carry energy away from the star, and over millions of years that energy loss causes the rotation to slow down. We have measured this. Pulsars, which are spinning neutron stars, are observed to slow down very gradually over time. The rate of slowdown tells us how much energy the star is radiating, and in some cases, we can directly detect the gravitational waves with instruments like LIGO and Virgo. The surface of a rapidly spinning neutron star is not a place where anything stays still. The rotation drags the magnetic field along with it, and the magnetic field drags ionized plasma in the thin atmosphere. Near the poles, where the magnetic field lines converge, particles are accelerated to nearly the speed of light. They spiral along the field lines and radiate energy in tight beams. If one of those beams sweeps past Earth, we see a pulse, a lighthouse in space. That is a pulsar. We will talk about pulsars in detail in the next chapter, but for now, what matters is that the surface environment of a spinning neutron star is not static. It is a dynamic churning system where magnetic forces, rotation and gravity are all competing to shape what happens. Let's go back to the teaspoon, because this is the image that sticks in people's minds. A teaspoon of neutron star material weighs 1 billion tons. You've probably heard that. It is one of the most repeated facts about neutron stars, and it is mostly true, but the number varies depending on whose estimate you trust and what you mean by a teaspoon. A teaspoon is not a precisely defined scientific unit. It is roughly 5 milliliters, 5 cubic centimeters. If you scoop up 5 cubic centimeters of material from the crust of a neutron star, where the density is around 1 billion kilograms per cubic meter, the mass would be about 5 billion kilograms, 5 million tons. If you scoop from deeper in the star, where the density is closer to 10 to the 17th kilograms per cubic meter, the same volume would weigh more, a lot more. Estimates range from 10 million tons on the low end to 1 billion tons or more on the high end, depending on the depth. The uncertainty comes from the fact that the density varies dramatically with depth, and we do not know the exact equation of state. But the basic point stands. A small volume of neutron star material, the kind of volume you could hold in your hand if it were water, contains more mass than the entire human population of Earth. Every person alive today, all 8 billion of us, if you could somehow weigh us all at once, would total less than the mass of a single teaspoon of neutron star matter. And if you somehow brought that teaspoon back to Earth, it would not sit politely on a table. It would fall through the table, through the floor, through the planet. The gravity holding the neutrons together inside the star is what keeps the matter stable. Remove that gravity, a neutron star material would explosively decompress. The neutrons would decay into protons and electrons. The whole thing would blow apart in a nuclear detonation that would make every bomb ever built look like a firecracker. You cannot bottle a neutron star. The material only exists in that form because it is being compressed by the weight of a star's worth of mass, pressing down on it from above. There is a thought experiment that gets passed around in physics circles. If you could somehow teleport a neutron star to Earth orbit, what would happen? The answer is nothing good. The neutron star would not hover there like a moon. It would fall. Not toward the Earth, because the Earth's gravity is negligible compared to the neutron stars. The Earth would fall toward it. The two objects would spiral together, and the Earth would be torn apart by tidal forces long before they collided. The neutron star's gravity would stretch the Earth into an elongated shape. The crust would crack, the oceans would be pulled off the surface, and the planet would disintegrate into a ring of debris orbiting the neutron star. Then the debris would rain down onto the star's surface over the course of a few hours, releasing enough energy in the process to briefly outshine the sun. The entire Earth, converted into heat and radiation by the gravitational well of an object 20 kilometers across. That is what 1 billion times Earth gravity does. Now let's imagine you could somehow observe the surface from a safe distance. You're in a heavily shielded spacecraft, far enough away that the tidal forces are manageable and the radiation is not immediately lethal. You look out the window. What do you see? The neutron star itself is bright, glowing blue-white from the heat, but it is also small. From a distance of, say, 1,000 kilometers, it would look like a point of light. A very bright point, but still just a point. You would need instruments to resolve it as a disk. Zoom in, and you would see that the surface is not uniform. There are hotspots, regions where the temperature is higher, where the magnetic field is funneling particles down and heating the crust. If the star is a pulsar, those hotspots might be near the magnetic poles, and as the star rotates, you would see the brightness flicker as the hotspots swing in and out of view. The rotation is fast enough that the flicker would be difficult to track with the naked eye. A few milliseconds per rotation in some cases. You would need high-speed cameras to see the pulses as distinct events. If the neutron star has an accretion disk, material falling onto it from a companion star, the view changes. The disk glows in X-rays as the infalling gas spirals down and heats up. Close to the neutron star, the disk is so hot that it emits high-energy radiation that would fry your instruments if you were not careful. The material does not fall straight down. It spirals, following the magnetic field lines, and when it finally hits the surface, it does so at nearly the speed of light. The impact releases a burst of energy. If the accretion is steady, the neutron star glows steadily in X-rays. If the accretion is uneven, you get bursts, type 1 X-ray bursts. These are thermonuclear explosions on the surface of the neutron star. The infalling material, mostly hydrogen and helium, piles up on the crust. The pressure and temperature at the base of the pile climb until the hydrogen ignites in a runaway fusion reaction. The entire surface of the star lights up in a flash of X-rays that lasts a few seconds to a few minutes. Then it fades, then the process starts over. Some neutron stars in binary systems undergo these bursts regularly, every few hours or days, depending on how fast the material is falling in. We have observed thousands of these bursts. They are a standard part of neutron star behavior in accreting systems, and what they tell us is that the surface of a neutron star is not a dead, inert place. It is active. Material falls in, the crust shifts, the magnetic field reconfigures, explosions happen, starquakes rattle the structure. The star is constantly responding to the immense forces acting on it. Gravity trying to crush it, rotation trying to fling it apart, magnetic fields trying to twist it into knots, and somehow the whole system holds together. Let's come back to the idea of standing on the surface, because it is worth emphasizing just how hostile the environment is. We talked about gravity and tidal forces and temperatures, but we have not talked about time. General relativity tells us that time runs slower in a gravitational field. The stronger the field, the slower the time. On Earth, the effect is negligible. A clock on the ground runs slightly slower than a clock in orbit, but the difference is only a few microseconds per day. On a neutron star, the effect is enormous. If you could somehow survive on the surface and you had a clock, and your friend was in a spacecraft far away with an identical clock, your clock would run noticeably slower. Time dilation. For every second that passes on the surface, more time passes for your friend. The exact ratio depends on the mass and radius of the neutron star, but it can be as much as 20 or 30%. If you spent an hour on the surface, your friend in the spacecraft would experience an hour and 15 minutes. This is not a small correction. This is time itself running at a different rate, because the curvature of space-time is so extreme. And if you tried to communicate, your signals would be redshifted. Like climbing out of the neutron star's gravitational well loses energy. Photons that leave the surface in the blue part of the spectrum arrive at the distant spacecraft shifted toward red. The shift is measurable. Astronomers use gravitational redshift to study neutron stars. By measuring how much the light is shifted, they can infer the strength of the gravitational field, and from that they can estimate the star's mass and radius. It is one of the few ways we have to measure the size of these objects directly. So the surface of a neutron star is not just a place, it is a different regime of physics. Time runs slower, space is curved, gravity is so strong that it changes the rules for how matter and energy behave. If you could somehow place a mirror on the surface and shine a light at it, the light would take longer to return than you would expect because time itself is dilated. If you dropped an object from a height of 1 meter, it would hit the surface in less than a microsecond, accelerating so fast that it would impact with more energy than a small bomb. The environment does not allow for slow, careful exploration. Everything happens fast and everything ends in destruction. There is one more thing worth mentioning. Neutron stars are not always alone. Many of them are in binary systems orbiting another star. If the companion is a normal star, material from the companion's outer layers can be pulled onto the neutron star by gravity. The process is called accretion, and it is messy. The infalling material does not land gently. It slams into the surface at relativistic speeds, heats up, and emits radiation. If the accretion rate is high enough, the neutron star can spin up. The material carries angular momentum, and when it lands, it transfers that angular momentum to the star. Over time, the star spins faster. This is how you get millisecond pulsars. Old neutron stars that have been spun up by accreting material from a companion, they are recycled. Resurrected from a slow spin to a fast spin by the death throes of a nearby star, And if the companion is another neutron star, things get even stranger. Two neutron stars orbiting each other lose energy to gravitational waves. The orbit shrinks. Over millions of years, the two stars spiral closer and closer until they collide. The collision is one of the most violent events in the universe. We have detected the gravitational waves from neutron star mergers. In 2017, the LIGO and Virgo detectors picked up a signal from two neutron stars colliding about 130 million light-years away. The signal lasted for about 100 seconds, during which the two stars orbited each other dozens of times, moving faster and faster as the orbit decayed. Then they merged. The gravitational wave signal cut off. A burst of gamma rays lit up the sky. Telescopes around the world swung to the location and detected the optical afterglow. It was the first time humanity had witnessed a neutron star merger, with both gravitational waves and electromagnetic radiation. And what we learned is that the collision was so energetic it forged elements heavier than iron. Gold, platinum, uranium. The debris scattered into space, enriching the surrounding gas with heavy elements. The same elements that would later be incorporated into planets and moons and eventually into jewelry and electronics, and the atoms in your body. So the surface of a neutron star is not just a curiosity. It is the site where some of the universe's most extreme processes happen, where gravity is strong enough to warp time, where rotation is fast enough to drag space, where matter is compressed past the point where atoms can exist, and where, occasionally, two of these objects collide and briefly become the brightest thing in the sky. We cannot visit the surface, we cannot land there, we cannot touch it, but we can observe it. We can measure it. And slowly we are learning what it means for matter to exist at the edge of collapse. The surface is not the end of the story, it is the beginning. Because above the surface, held in place by magnetic fields that are strong enough to bend spacetime, some neutron stars emit beams of radiation so intense they can be detected across thousands of light-years. Those beams sweep around like lighthouses, and when one of them sweeps past Earth, we see a pulse. That is where we go next. So we left the surface of a neutron star, that impossible compressed hellscape, where time runs slow and matter exists in a form that has no business being stable. We talked about gravity strong enough to flatten mountains into millimeter bumps and temperatures that would vaporize normal matter before it ever arrived. And now we need to talk about what happens above that surface. Because some neutron stars do not just sit there glowing quietly in the darkness. Some of them scream. They emit beams of radiation so intense, so focused, and so precisely timed that when we first detected them, we thought they might be artificial. Signals from an alien civilization trying to get our attention. They were not. But what they actually were turned out to be stranger than anyone predicted. And the woman who found them did not get the credit she deserved until decades later. The year is 1967. The place is Cambridge, England. A graduate student named Jocelyn Bell Burnell is working at the Mullard Radio Astronomy Observatory under her advisor, Anthony Hewish. She has spent 2 years helping to build a radio telescope designed to detect quasars, those bright, distant, feeding supermassive black holes we talked about earlier. The telescope is not elegant. It is 4.5 acres of wire and poles, more than 2,000 of them, strung together in a field. The whole thing looks like a construction accident, but it works. It is sensitive to radio waves, and it scans the sky continuously, recording signals on long rolls of paper that spool out of chart recorders at a steady pace. Bell's job is to analyse those charts, miles of paper, every day, looking for patterns. In August 1967, she notices something odd, a bit of scruff in the data, a brief burst of radio noise that does not look like normal interference. She marks it, moves on. It shows up again a few weeks later. Same spot in the sky, same time of day. She starts paying closer attention. By November, she has isolated the signal. It is repeating, every 1.33 seconds like clockwork, a pulse, then silence, then another pulse, then silence, over and over. The signal is so regular that she can set her watch by it. Hewish is skeptical at first. Radio interference is everywhere. Satellites, radar, electrical equipment, all of it shows up in the data as noise. But this signal is different. It only appears when the telescope is pointed at a specific part of the sky. It does not drift like a satellite. It does not fade like atmospheric noise. It is coming from a fixed location in space, and the timing is absurdly precise. 1.33 seconds between pulses, accurate to within a fraction of a millisecond. No natural process they knew of could produce a signal that regular. The team runs through every possible explanation. Could it be a satellite? No. The signal is too faint and the source is not moving. Could it be some kind of terrestrial interference reflecting off something in orbit? No. The timing does not match any known human activity. Could it be a mistake in the equipment? No. They built the telescope themselves and they know exactly how it works. The signal is real. It is astronomical. And it is repeating with a precision that nothing in nature should be able to maintain. Bell writes in her notes that the signal is so unusual they jokingly start calling it LGM-1. Little Green Men 1. The implication being that maybe, possibly, they have stumbled onto a beacon from an extraterrestrial intelligence. Nobody actually believes that, but nobody has a better explanation either. Then Bell finds a second signal, different location in the sky, different pulse rate, then a third, then a fourth, all of them pulsing at regular intervals, all of them coming from fixed points in space, all of them far too precise to be random noise. If these were alien beacons, the galaxy was apparently full of them. That explanation stops sounding plausible very quickly. The alternative is that there is some kind of natural astrophysical object out there that can produce a perfectly timed radio pulse. But what object? Stars do not pulse that fast. Planets do not emit radio waves like that. Galaxies certainly do not tick like metronomes. It takes months of analysis and consultation with theorists before someone makes the connection. The only object that could spin fast enough to produce pulses at those rates without flying apart would be something extraordinarily small and extraordinarily dense. A white dwarf is too big. It would tear itself apart at those rotation speeds. The only thing left in the theoretical toolkit is a neutron star, and neutron stars, as we now know, had been predicted back in 1934 but never observed. Most astronomers assumed they were probably real, but finding one seemed impossible because they are so small, 20 kilometers across. You would need extraordinary luck to spot one unless it happened to be doing something loud. Turns out they are doing something loud. They are broadcasting. The pulsing signal is not coming from the body of the star itself. It is coming from beams of radiation emitted along the star's magnetic poles. Neutron stars have magnetic fields, strong ones, trillions of times stronger than Earth's magnetic field, and like Earth, the magnetic axis does not always line up with the rotation axis. Picture a spinning top where the magnetic north pole is tilted off to the side. As the top spins, the magnetic pole sweeps around in a circle. Now imagine that magnetic pole is so strong, it accelerates charged particles to nearly the speed of light. Those particles, mostly electrons, spiral along the magnetic field lines and radiate energy in tight beams. If one of those beams happens to sweep across Earth, we see a pulse. If the beam misses us, we see nothing. The neutron star is still there, still spinning, still broadcasting, but the lighthouse beam is pointed somewhere else. This is the lighthouse model of pulsars, and it explains everything. The regularity comes from the rotation. Neutron stars spin fast because they conserve angular momentum during the collapse. A normal star rotates slowly, maybe once every few weeks. When the core collapses down to 20 kilometers, the rotation speeds up dramatically. An ice skater pulling in their arms. The result is an object that can spin hundreds of times per second without breaking apart because the gravity is strong enough to hold it together. The beams come from the magnetic poles. The timing is precise because the rotation is stable. And the reason we did not find these objects earlier is because we were not looking at radio wavelengths with sensitive enough equipment. Once we knew what to look for, we started finding them everywhere. Bell and Hewish published their discovery in February 1968. The paper was titled Observation of a Rapidly Pulsating Radio Source, and it changed astronomy. Within months, other teams found more pulsars. Within a year, dozens had been catalogued. The name Pulsar, a portmanteau of pulsating star, stuck. And in 1974, Hewish was awarded the Nobel Prize in Physics for the discovery. Bell was not. The prize went to Hewish and another astronomer, Martin Ryle, who had developed radio telescope technology. Bell, who had actually found the signals and spent months carefully analysing them and ruling out interference, was left out. The omission was controversial at the time, and it remains controversial today. Bell herself has been gracious about it, noting that as a graduate student she was in a subordinate role, and the prize traditionally goes to senior researchers, but the astronomical community has largely come around to the view that she was robbed. In recent decades, she has received numerous awards and honours in recognition of her work, and she's now widely credited as the discoverer of pulsars. History corrected itself slowly. The discovery of pulsars confirmed that neutron stars were real, and it opened up an entirely new field of study. Because once you know pulsars exist, you can start measuring them, and the measurements are wild. The first pulsar Bell found, now called PSR B 1919+21, pulses every 1.33 seconds. That means it is rotating once every 1.33 seconds. Not fast by neutron star standards, but fast enough to be immediately bizarre. A star with more mass than the Sun spinning once per second. The equator of that star is moving at thousands of kilometers per second. Not quite relativistic, but getting there. And the pulses are so precise that over the course of a year, the timing error is measured in microseconds. You could use a pulsar as a clock. In fact, astronomers do. Pulsar timing is one of the most precise measurement techniques in all of science. Then we started finding faster ones. Much faster. The current record holder, PSR J 174.8-2.446 AD, spins 716 times per second. That is not a typo. 716 rotations every second. The equator of that neutron star is moving at roughly 24% the speed of light. At that speed, the centrifugal force is trying to rip the star apart. The only thing keeping it together is gravity and the structural integrity of neutron degenerate matter. If you spun it any faster, the surface would start to shed material. There is a maximum rotation rate, somewhere around 1,000 times per second, depending on the mass and radius of the star. Push past that and the star disintegrates. We have not found anything spinning faster than 716 yet, but we are looking. Millisecond pulsars like that one are in a class of their own. They are old neutron stars that have been spun up by accreting material from a companion star. The process is called recycling. The neutron star starts out spinning relatively slowly, a few times per second, which is already absurdly fast by normal star standards, but slow for a neutron star. Then it enters a binary system with a normal star. The companion star ages, expands, and starts shedding its outer layers. The neutron star pulls that material in. The infalling gas carries angular momentum, and when it lands on the neutron star, it transfers that momentum to the star. The star spins faster. Over millions of years of steady accretion, the neutron star can spin up from a few rotations per second to hundreds. The companion star, meanwhile, gets stripped down to a white dwarf or evaporates entirely. What is left is a millisecond pulsar spinning at absurd speeds, alone or in a tight orbit with the remnant of its former companion. These fast pulsars are incredibly useful as astronomical tools, because they spin so fast and so regularly. Any deviation in the pulse timing tells you something is affecting the pulsar. If the pulsar is in a binary system, the orbit causes the pulses to arrive slightly early or slightly late, depending on where the pulsar is in its orbit. Doppler shift. By measuring those timing variations, astronomers can map the orbit with extraordinary precision: mass of the companion, orbital period, eccentricity, even the orientation of the orbit in three-dimensional space. Pulsar timing has been used to discover planets around neutron stars, detect gravitational waves from distant black hole mergers, and test general relativity to levels of precision that no other method can match. But not all pulsars are radio emitters. Some of them shine in X-rays. X-ray pulsars are typically neutron stars in binary systems, where material from the companion star is falling onto the neutron star. The infalling gas heats up as it spirals down the magnetic field lines and slams into the magnetic poles. The impact regions, called hotspots, glow in X-rays. As the neutron star rotates, the hotspots swing in and out of view and we see pulses. The mechanism is similar to radio pulsars, but the energy source is different. Radio pulsars are powered by the rotational energy of the star itself. They are gradually spinning down as they emit radiation. X-ray pulsars are powered by accretion. They can spin up or spin down depending on how much material is falling in and from what direction. Then there are the magnetars. And this is where things get truly strange. Magnetars are neutron stars with magnetic fields so strong they break the standard pulsar model. A typical neutron star has a magnetic field around 1 trillion Gauss. For reference, The Earth's magnetic field is about half a Gauss. A refrigerator magnet is about 100 Gauss. A typical neutron star is a trillion Gauss. Magnetars are around 1 quadrillion Gauss, 10 to the 15th. That is 1,000 times stronger than a normal neutron star, and at those field strengths, the magnetic field starts doing things that ordinary magnetism does not do. The field is strong enough to distort atoms. Electrons in the magnetosphere do not orbit nuclei the way they do in normal matter. They get stretched into elongated shapes, squeezed into narrow cylinders by the magnetic pressure. The field is strong enough to affect the vacuum itself. Empty space near a magnetar becomes birefringent, meaning light travelling through it splits into two beams with different polarizations. The field is strong enough to warp space-time, not as much as the neutron star's gravity does, but measurably. General relativity predicts that strong magnetic fields contribute to space-time curvature, and in the case of magnetars, the contribution is significant enough to show up in the data. Magnetars do not behave like normal pulsars. They do not spin as fast. Most of them rotate once every few seconds, much slower than typical radio pulsars, and they do not emit steady beams of radio waves. Instead, they flare. Occasionally, violently and without much warning, a magnetar will release a burst of X-rays or gamma rays. The energy output during one of these flares can exceed the total energy the Sun emits in a year, in a few seconds. The flares are thought to come from starquakes, cracks in the crust caused by the immense magnetic stresses twisting the star's structure. When the crust fractures, magnetic field lines snap and reconfigure. The reconfiguration releases energy in the form of high-energy photons, a magnetar flare. The most powerful magnetar event on record happened on December 27, 2004. A magnetar called SGR 1806-20, located about 50,000 light-years away on the far side of the Milky Way, released a giant flare. The flare lasted about 1/10 of a second. In that brief moment, it emitted more energy than the Sun produces in 100,000 years. The burst of gamma rays hit Earth's upper atmosphere and ionized part of it, temporarily disrupting radio communications. Satellites in orbit detected the flash and several of them were temporarily blinded. The detectors were saturated, overloaded. For a brief instant, a star 50,000 light-years away released enough energy to affect instruments orbiting our planet. That is the power of a magnetar. The flare was so bright that if the magnetar had been located at the distance of the Moon, about 400,000 kilometers away, the gamma-ray burst would have delivered a radiation dose high enough to cause mass extinctions on Earth. Every living thing on the daylight side of the planet would have been exposed to lethal levels of radiation. The atmosphere would have been stripped, the ozone layer destroyed. It would have been an extinction-level event. Fortunately, the magnetar was 50,000 light-years away. We got a light show, nothing more. But it raises an uncomfortable question. How many of these things are out there? And how often do they go off? We have detected about 30 confirmed magnetars in the Milky Way. That is a tiny fraction of the total neutron star population, which is estimated at around 100 million. Most neutron stars are not magnetars. Most of them have normal, merely trillion Gauss magnetic fields. But magnetars exist. They are rare, but they are real. And if one happened to be located within a few thousand light-years of Earth, and it went off, the results would not be pleasant. We would not die instantly. The atmosphere would shield us from the worst of the immediate radiation, but the long-term effects, ozone depletion, increased UV radiation, disruption of the food chain, would be severe. Fortunately, none of the known magnetars are close enough to cause that kind of damage. The nearest confirmed magnetar is about 9,000 light-years away, uncomfortably close on galactic scales, but far enough that even a giant flare would not threaten life on Earth. Still, the fact that magnetars exist at all is unsettling, because we do not entirely understand why some neutron stars have normal magnetic fields and others have fields 1,000 times stronger. The leading theory is that magnetars are young. When a massive star collapses, the core is rotating rapidly, and the collapse amplifies any existing magnetic field. If the conditions are just right, the field can be amplified by a factor of 1,000 or more through a dynamo process in the first few seconds after the neutron star forms. The result is a magnetar. Over time, the field decays. Magnetars are thought to have lifetimes of around 10,000 years before the field drops back down to normal neutron star levels, and they stop being magnetars. That is a blink on cosmic timescales, which means every magnetar we see today is a very young neutron star, still glowing hot from its formation, still crackling with magnetic energy, and still capable of flaring without warning. The connection between pulsars and magnetars is not clean. They are both neutron stars. They both have strong magnetic fields, but the field strength makes all the difference. A normal pulsar is powered by rotation. A magnetar is powered by its magnetic field. As the field decays, it releases energy. That energy heats the star, drives the flares, and gradually spins the star down. Magnetars lose rotational energy much faster than normal pulsars because the magnetic field is constantly doing work, twisting the crust, heating the interior, accelerating particles. Over time, a magnetar slows down, the field weakens, the flares stop, and what is left is a slowly spinning neutron star with a magnetic field that is merely a trillion Gauss instead of a quadrillion. Ordinary, unremarkable, just another dead star sitting in the darkness. But while they are active, magnetars are among the most extreme objects in the universe, stronger magnetic fields than any other known object, flares that outshine entire galaxies for a fraction of a second, and rotation rates that are slower than normal pulsars but still fast enough to complete a full spin in a few seconds. If you could somehow watch a magnetar up close, assuming you were in a heavily shielded spacecraft and parked at a very safe distance, you would see a glowing sphere about 20 kilometers across, spinning once every few seconds, surrounded by a haze of ionized particles trapped in the magnetic field. Occasionally, the surface would crack, the magnetic field lines would snap, and a burst of X-rays and gamma rays would light up the surrounding space. Then it would settle down, for a while, until the stresses built up again and another crack formed. Living near a magnetar would be like living next to a bomb that goes off at random intervals. You could go years without an incident. Then one day, without warning, the sky lights up and everything electronic stops working. Not a good neighborhood. So pulsars and magnetars are both neutron stars, but they occupy different parts of the neutron star family tree. Pulsars are the steady, reliable ones. They spin fast, they emit regular beams of radio or X-rays, and they slow down gradually over millions of years as they radiate energy. Magnetars are the violent, unpredictable ones. They have stronger magnetic fields, they flare without warning, and they decay on much shorter timescales. Both types are powered by the fundamental properties of neutron stars: extreme density, extreme gravity, extreme magnetic fields, and both types have taught us an enormous amount about physics at the edge of what matter can do. The lighthouse effect, the sweeping beam of radiation from a spinning magnetic field, is one of the most elegant phenomena in astrophysics. It is simple, a misaligned magnetic axis on a rotating object. That is all it takes. But the result is a signal so precise, so regular, and so detectable across vast distances that it turned neutron stars from a theoretical curiosity into one of the most studied classes of objects in the sky. We have found thousands of pulsars now. Radio pulsars, X-ray pulsars, gamma-ray pulsars, each one a rotating neutron star, each one a natural laboratory where we can test physics in conditions we could never replicate on Earth. And the precision of pulsar timing has opened up applications nobody predicted. Pulsar timing arrays, networks of telescopes monitoring dozens of millisecond pulses simultaneously, are being used to detect gravitational waves at frequencies too low for LIGO to see. When a gravitational wave passes through the galaxy, it stretches and compresses space very slightly. That stretching and compression changes the distance between Earth and the pulsars, which changes the arrival time of the pulses by a few nanoseconds. By monitoring many pulsars at once and looking for correlated timing shifts, astronomers can detect gravitational waves from supermassive black hole binaries millions of light years away. The technique is called Pulsar Timing Array Gravitational Wave Detection, and it is one of the most ambitious experiments in modern astronomy, using dead stars as sensors to detect ripples in space-time from black holes we cannot see. That is what pulsars have become: tools, clocks, laboratories. All because one graduate student in 1967 noticed a bit of scruff in her data and decided to investigate. But pulsars are not the only signals coming from neutron stars, because while we have been studying these rotating lighthouses and cataloguing their spins and mapping their magnetic fields, something else has been happening. Signals that do not fit the pulsar model, bursts of radio waves that repeat at irregular intervals, flashes of energy that come from neutron stars but do not follow the neat, predictable pattern of a rotating beam. Signals that, once again, made astronomers wonder if something stranger was going on. And that is where we go next. Because neutron stars, it turns out, are not finished surprising us. We left off talking about lighthouses, neutron stars spinning so fast and beaming radiation so precisely that you could set your watch by them. Pulsars discovered by a graduate student who noticed a bit of scruff in her data and had the discipline to follow it until the scruff turned into one of the most important discoveries in 20th century astronomy. Magnetars that twist themselves into knots and occasionally release more energy in 1/10 of a second than the Sun produces in 100,000 years. All of it explainable. All of it fitting neatly into models we could test and refine and eventually understand. The universe was behaving. And then, as it tends to do just when we think we have things figured out, it stopped. Because while astronomers were busy cataloguing pulsars and measuring their spin-down rates, and using them as cosmic clocks, something else started showing up in the data. Brief flashes of radio energy. Not from pulsars, not following any predictable pattern, just sudden bursts of radio waves, intensely bright, lasting only a few milliseconds, and then gone. The first one was detected in 2007, buried in archival data from the Parkes radio telescope in Australia. The astronomer who found it, Duncan Lorimer, was not even looking for it. He was searching through old observations, training software to identify interesting signals, and the software flagged something that made no sense. A burst of radio emission that lasted less than 5 milliseconds, bright enough to outshine the entire radio sky for that brief moment, and coming from a location billions of light years away. The signal was so strange that Lorimer and his team spent months checking for errors before publishing. Satellite interference, lightning, a truck driving past the telescope. Nothing fit. The burst was real. It was cosmic, and it had released more energy in 5 milliseconds than the Sun emits in an entire day. They called it a fast radio burst. The name is bland but accurate. Radio waves, very fast, burst, done. That first one got the designation FRB 01.2724, named for the date it was recorded, July 24th, 2001. For a while, it stood alone. One unexplained flash in the data. Interesting, sure, but also possibly a fluke. One-off events are hard to study. You cannot go back and observe the source again because by the time you know it happened, it is already over. The source could have been anything. A neutron star exploding, 2 black holes colliding, some exotic event we had never seen before. Without more data, the speculation was endless and useless. Then more started showing up. Another burst in 2012, another in 2013. By 2015, radio telescopes around the world were detecting fast radio bursts at a rate of a few per year, and the pattern, or rather the lack of one, was maddening. Some bursts came from nearby galaxies, some from halfway across the observable universe. Some were single flashes, never repeating. Others, and this is where things got truly strange, came from the same spot in the sky multiple times. Repeaters. The existence of repeating fast radio bursts changed everything, because a one-time burst could be anything. A cataclysm, a star exploding in some weird way, an event so violent it destroys the source entirely. But a repeating burst means the source survives. It is still there, still capable of generating these absurdly energetic flashes, and that ruled out most of the catastrophic models. Whatever is making these bursts is not being destroyed in the process. The first confirmed repeating FRB was designated FRB 12M1/2. The number tells you when it was discovered, November 2nd, 2012. It was detected by the Arecibo telescope in Puerto Rico, that massive radio dish that collapsed in 2020 after decades of service. The burst itself was unremarkable by FRB standards, a few milliseconds of intense radio emission, bright and brief. What made it special came later. In 2015, the same source flashed again, then again, then again. Over the next few years, astronomers detected more than 200 bursts from the same location. Not periodic, not following a clock like a pulsar. Just occasional flashes, sometimes days apart, sometimes weeks, completely unpredictable. The source was localized to a dwarf galaxy, about 3 billion light-years away. A small, faint, star-forming galaxy. Nothing about it looked unusual except for the fact that something inside it was occasionally screaming at us in radio waves. The leading theory, and the one that fits the data best so far, is that at least some fast radio bursts are coming from magnetars, those hypermagnetized neutron stars we talked about earlier, the ones with magnetic fields a quadrillion Gauss strong, the ones that occasionally crack their own crusts and release flares of X-rays and gamma rays. The model goes like this. A magnetar's magnetic field is so strong it twists the star's structure. The crust is under constant stress. Occasionally the stress becomes too much. The crust fractures, a starquake. The magnetic field lines snap and reconnect, releasing a burst of energy. Most of that energy comes out as X-rays and gamma rays, but if the conditions are just right, if the magnetic field configuration happens to be aligned in a specific way, some of the energy gets converted into a coherent burst of radio waves, a fast radio burst. The burst lasts only a few milliseconds because the timescale for magnetic reconnection is incredibly short. Then it is over, the magnetar settles down, until the stresses build up again and another crack forms, another burst. This model explains why some FRBs repeat. The magnetar is still there. It is not destroyed by the burst. It just sits there, occasionally cracking, occasionally flashing, like a cosmic lighthouse that does not know how to keep a schedule. It also explains why FRBs are so bright. Magnetars are among the most energetic objects in the universe. A single flare can release more energy than the sun produces in years. If even a tiny fraction of that energy gets funneled into a radio burst, the result would be exactly what we see. A brief intense flash visible across billions of light years. The model has problems, of course. Not all FRBs repeat. Some sources flash once and never again, as far as we can tell. Maybe those are coming from magnetars that only crack once, or maybe they are coming from something else entirely. Neutron stars merging, black holes doing something weird, some process we have not thought of yet. The field is still young. We have detected thousands of FRBs now, but we have only localized a handful to specific galaxies, and we have only identified a repeating source in a few cases. The data is growing, but the mystery is not solved. And then there is the 22-minute signal. This one is different. Not a burst, not a flash. A repeating pulse, like a pulsar, except no pulsar should behave this way. The signal was detected in 2022, coming from a source designated GLEAM X J1 Sisinsk 2759.5, van de Vituduthrus van Visum 04.3, which is a mouthful, so let's just call it GLEAM X. The name comes from the survey that found it, the Galactic and Extragalactic All-Sky MWA survey, conducted using the Murchison Wide Field Array in Western Australia. GLEAM X emits a pulse of radio energy every 22 minutes, roughly. The timing is not perfectly regular, which immediately disqualifies it from being a normal pulsar. Pulsars are precise. Their periods are stable to within microseconds over years. GLEAM X drifts. Sometimes the pulse comes a little early, sometimes a little late, but on average, every 22 minutes, it lights up in radio waves for about a minute, then goes quiet. 22 minutes is far too long for a pulsar. Pulsars spin. The fastest ones complete hundreds of rotations per second. The slowest ones we have ever found spin once every few seconds. A 22-minute rotation period would mean the neutron star is spinning incredibly slowly. So slowly that the mechanism powering normal pulsars should not work. Pulsars are powered by their rotational energy. As they spin, they emit beams of radiation, and that radiation carries energy away. The star slows down. The slower the spin, the less energy available to power the emission. Below a certain threshold, the pulsar shuts off. It becomes too faint to detect. The cutoff is somewhere around a few seconds. Spin slower than that and the pulsar should be dead. GLEAM X is spinning once every 22 minutes and it is still flashing. Bright enough to be detected across interstellar distances. That does not fit. One possibility is that GLEAM X is not a normal neutron star. It could be a white dwarf. White dwarfs are less dense than neutron stars, about 1 million times less dense, and they are much larger. Earth-sized instead of city-sized. A white dwarf can have a strong magnetic field, not as strong as a neutron star, but strong enough to channel particles and create beams of radiation. And because white dwarfs are larger, they can spin more slowly without the surface breaking apart. A 22-minute rotation period for a white dwarf is unusual, but not impossible. The problem with this explanation is that the emission from Glimex is too bright. White dwarfs do not generate enough energy to produce the kind of radio burst we're seeing, unless something else is powering them. Accretion, maybe. Material falling onto the white dwarf from a companion star. But Glimex does not have a detected companion, and the bursts do not look like accretion-powered emission. They look like something else. Another possibility is that Glimex is a neutron star, but it is being powered by something other than rotation. Magnetic energy, perhaps. If the neutron star has an unusually strong magnetic field, even for a neutron star, the field itself could store enough energy to power occasional bursts of emission. The field would decay slowly over time, releasing energy in pulses. Not because the star is spinning and sweeping a beam past us, but because the magnetic field is doing work, twisting, reconnecting, heating the surrounding plasma. This is essentially the Magnetar model again, but applied to a much slower process. Instead of violent flares lasting milliseconds, you get slower, more regular pulses lasting minutes. The timing would be controlled not by rotation but by the dynamics of the magnetic field. How fast it reconnects, how much energy it releases per event. The irregularity in the timing could come from the fact that magnetic reconnection is not a perfectly periodic process. It depends on the local conditions in the magnetosphere, which change over time. We do not know. Glimex has been observed for a limited time, and the number of similar objects we have found is still small. There are a few other candidates, objects that emit radio pulses on timescales of minutes to hours. Not enough to call it a population, not enough to build a solid theory. What we can say is that these objects exist. They are out there. They do not fit neatly into the pulsar category, or the magnetar category, or the white dwarf category. They are something in between, or something new. And the fact that we keep finding objects that do not fit the existing boxes tells us the taxonomy of neutron stars and their relatives is incomplete. We thought we had mapped the landscape. Pulsars here, magnetars there, dead neutron stars over in the corner. Turns out the landscape is bigger and stranger than we thought, and Glimex is sitting in a region of that landscape we did not know existed until a few years ago. Now let's talk about Geminga. The name sounds like something out of science fiction. It is not. It is Milanese dialect, a contraction of Geminga, which translates roughly to "it's not there." The name was given in the 1980s when astronomers were trying to figure out what Geminga actually was. They could see it in gamma rays, a bright source in the constellation Gemini, hence Geminga. But when they looked for it in other wavelengths, radio, optical, X-ray, there was nothing. No star, no nebula, no obvious counterpart. It was there in gamma rays and nowhere else. Geminga, it's not there. The name stuck. Eventually better instruments and more observations revealed that Geminga is a neutron star, an isolated one, no companion star, no supernova remnant nearby, just a lone neutron star sitting about 800 light-years from Earth, spinning once every quarter of a second and emitting beams of gamma rays from its magnetic poles. It is a pulsar technically, but it is a gamma-ray pulsar. The beams are not in the radio band, they are at much higher energies, which is why the early radio telescopes missed it. The star itself is old by neutron star standards, around 300,000 years, old enough that it has cooled down and faded in most wavelengths, but it is still spinning, still beaming, still detectable if you look in the right energy range. What makes Geminga interesting beyond the name is what it is doing to the space around it. Neutron stars spin. We have established that. As they spin, they drag their magnetic fields around with them. The magnetic field accelerates charged particles, mostly electrons and protons, to nearly the speed of light. Those particles stream outward, forming what is called a pulsar wind. The wind is not made of gas or atoms. It is made of relativistic particles and magnetic fields, a plasma moving at a significant fraction of the speed of light. As the wind expands, it eventually runs into the surrounding interstellar medium, the gas and dust drifting through space. When the wind hits that material, it slows down. The kinetic energy of the particles gets converted into radiation. The result is a pulsar wind nebula, a glowing cloud of high-energy particles surrounding the neutron star powered by the star's rotation, visible in X-rays and sometimes gamma rays. Geminga has a pulsar wind nebula. It is faint, hard to detect, but it is there. And in 2017, observations from the High Altitude Water Cherenkov Observatory (HLWC) in Mexico revealed something unexpected. The nebula is not just emitting gamma rays, it is producing cosmic rays. High-energy particles, mostly protons and electrons, accelerated to energies far higher than anything we can produce in particle accelerators on Earth. And mixed in with those cosmic rays is antimatter, positrons, the antimatter counterpart of electrons. Same mass, opposite charge. Antimatter is not science fiction. It is real. It has been detected, created in laboratories, observed in space. When a positron meets an electron, they annihilate. Both particles disappear, and their mass converts directly into energy in the form of gamma rays. Einstein's equation in action, E = mc squared. Antimatter annihilation is one of the most efficient energy release mechanisms in the universe, far more efficient than nuclear fusion, which is why antimatter engines show up in science fiction so often. In principle, if you could store antimatter and bring it into contact with matter in a controlled way, you could build a rocket or a power plant that makes our current technology look like a candle next to a floodlight. In practice, storing antimatter is almost impossible. It annihilates the moment it touches normal matter, and there is no such thing as an antimatter container. Any container you build is made of normal matter. The moment you put antimatter inside, it touches the walls and explodes. You would need to suspend it using magnetic fields in a perfect vacuum, and even then, stray particles would eventually find their way in and trigger annihilation. It is a hard problem. We can make small amounts of antimatter in particle accelerators, a few atoms at a time, and we can hold on to them for a few seconds before they annihilate. But building anything practical out of antimatter is far beyond our current capabilities. Geminga, however, does not have that problem. It is producing positrons naturally, not a few atoms, not a controlled lab experiment, a steady stream of antimatter particles flowing out from the Pulsar Wind Nebula, mixing with the interstellar medium, and eventually annihilating when they find electrons to collide with. The positrons are produced by the same mechanism that produces the gamma rays. Relativistic particles in the pulsar wind collide with photons, high-energy collisions. When a photon and a relativistic electron collide, the photon can convert into a particle-antiparticle pair, an electron and a positron. This process, called pair production, happens all the time in high-energy astrophysics, near black holes, in supernova remnants, anywhere you have photons and particles moving at relativistic speeds. Geminga's Pulsar Wind Nebula is a natural particle accelerator. It is taking the rotational energy of the neutron star, converting it into kinetic energy of particles, and those particles are colliding with the surrounding light and matter to produce gamma rays, X-rays, and antimatter. The discovery that Geminga is producing positrons was not entirely surprising. Physicists had predicted for decades that pulsar wind nebulae should be sources of antimatter. What was surprising was the amount. Observations from HWC and from space-based detectors like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station showed that Geminga and a few other nearby pulsars are producing far more positrons than the models predicted. Not a little more, a lot more. Enough that they might account for a significant fraction of the positrons detected in cosmic rays hitting Earth's atmosphere. Cosmic rays are high-energy particles that constantly bombard Earth from space, mostly protons, some heavier nuclei, and a small fraction, about 1%, are positrons. For a long time, that 1% was a mystery. Normal cosmic ray sources, supernova remnants and the like, do not produce much antimatter. They accelerate protons and electrons, sure, but positrons are rare, unless you have a mechanism specifically designed to create them. Pulsars, it turns out, are exactly that mechanism. The Pulsar Wind Nebula around Geminga is a positron factory, and because Geminga is relatively close to us, only 800 light-years away, the positrons it produces can reach Earth. They drift through the interstellar medium for hundreds of thousands of years, spreading out, losing energy, but some of them eventually make it to our solar system. When they do, our instruments detect them, and for years astronomers were puzzled by the fact that we were detecting more positrons than the standard models predicted. Geminga and a handful of other nearby pulsars are the explanation. They are pumping antimatter into the local cosmic ray population. Not enough to be dangerous. The flux is tiny, but enough to show up in the data and solve a long-standing puzzle. The fact that a neutron star 800 light-years away is producing antimatter that we can detect here is strange enough, but the numbers make it even stranger. Geminga is not particularly unusual as neutron stars go. It is a fairly typical middle-age pulsar. There are thousands of similar objects in the Milky Way. If Geminga is producing this much antimatter, and other pulsars are doing the same, then the galaxy is full of antimatter sources we barely noticed until recently. And the positrons they produce are mixing with the normal matter in the interstellar medium, annihilating, releasing gamma rays, and contributing to the diffuse glow of high-energy radiation that fills the galaxy. We thought that glow came mostly from supernova remnants and the interactions between cosmic rays and interstellar gas. Turns out pulsars are playing a bigger role than we realized. The detection of antimatter from Geminga also opens up another question. If pulsars are producing positrons, are they producing other forms of antimatter? Antiprotons, for example. The antimatter counterpart of protons, heavier, harder to produce, but not impossible. The same pair production process that creates electron-positron pairs can, at higher energies, create proton-antiproton pairs. The threshold energy is much higher because protons are nearly 2,000 times heavier than electrons. But in the extreme environment of a pulsar wind nebula, where particles are being accelerated to energies millions of times higher than their rest mass, antiproton production is possible. And if it is happening, those antiprotons would also drift through the galaxy, eventually reaching Earth and showing up in cosmic ray detectors. We have detected antiprotons in cosmic rays. Not many. They are rare, but they are there. And the question is, where are they coming from? Pulsars are one candidate, but the models are still uncertain. The data is still sparse. This is an active area of research. Every new observation, every new pulsar wind nebula mapped in gamma rays gives us another data point, another constraint on how much antimatter is being produced and where it is going. The broader point is this: neutron stars are not just dense, they are not just spinning, they are active, they're doing things, accelerating particles, producing radiation, creating antimatter, shaping the environment around them in ways we are only beginning to understand. Geminga is a case study, a single object, close enough to study in detail, strange enough to reveal processes that are probably happening around thousands of other neutron stars we cannot see as clearly. The fact that we can detect positrons from a neutron star 800 light-years away is not just a neat trick. It is evidence that neutron stars are contributing to the cosmic ray population in ways we did not account for until very recently. And if the positron excess we see in cosmic rays is coming from pulsars, that changes how we model the interstellar medium, how we understand particle acceleration in astrophysical environments, and how we think about the distribution of antimatter in the galaxy. Fast radio bursts, the 22-minute signal, Geminga's antimatter production. These are not unrelated curiosities. They are all symptoms of the same underlying reality. Neutron stars are extreme objects operating in regimes of physics we can barely model, and they are producing signals we're only just learning to detect. For decades, we thought we understood neutron stars. Pulsars, sure. Those made sense. Lighthouse beams sweeping past Earth at predictable intervals. We could measure them, time them, use them as clocks. They fit into the framework, but the more sensitive our instruments become, the more signals we find that do not fit. Bursts that repeat irregularly, pulses that come every 22 minutes when they should not be coming at all, antimatter streaming off nearby pulsars in quantities the models did not predict. Each new detection is a hint that the picture is incomplete, and the uncomfortable part is that we do not know what we are missing. Fast radio bursts could be magnetars, or they could be something else. White dwarfs doing something weird. Neutron stars with exotic magnetic field configurations we have not thought of. Some entirely new class of object we do not have a name for yet. The 22-minute signal could be a slow-spinning neutron star powered by magnetic energy. Or it could be a white dwarf with an unusually strong field. Or it could be a binary system where something is periodically eclipsing the emission. We have models, we have guesses, but we do not have certainty. And Geminga's antimatter production, while explainable in broad strokes, still has details that do not quite match the predictions. The amount of antimatter, the energy spectrum of the positrons, the spatial distribution of the pulsar wind nebula. All of it fits well enough to say we're on the right track. None of it fits perfectly enough to say we understand it completely. That is the frontier. Not the things we know, the things we almost know. The signals that are just strange enough to resist easy explanation, but not so strange that we can dismiss them as errors. Fast radio bursts were dismissed as errors for years. Too bright, too brief, too inconsistent with anything we expected. Until we found enough of them that dismissing them was no longer an option. The 22-minute signal is new enough that some researchers are still skeptical. Maybe it is an instrumental artifact. Maybe it is interference from a satellite. Maybe it will turn out to be mundane. But maybe it will not. And if it does not, if it turns out to be real and we keep finding more objects like it, then we will have to expand the taxonomy of neutron stars to include a category we did not know existed. Slow pulsars, magnetically powered emitters, something. Geminga is real. The Antimatter is real. The Pulsar Wind Nebula is real. The physics is understood well enough that we can model it, predict it, and match the observations to within a factor of 2 or 3, which, in astrophysics, counts as pretty good agreement. But factors of 2 or 3 matter. They mean the model is incomplete. There is something happening that we are not accounting for. Maybe the magnetic field structure is more complicated than we thought. Maybe the particle acceleration is more efficient. Maybe there is a population of cosmic rays we are not detecting that is carrying away energy we are not tracking. Small uncertainties, but they add up. And the broader implication is that neutron stars, for all the decades we have spent studying them, are still capable of surprising us. We have catalogued thousands of pulsars. We have measured their masses and radii with increasing precision. We have detected gravitational waves from neutron star mergers and used those signals to probe the equation of state of nuclear matter. We have mapped pulsar wind nebulae in X-rays and gamma rays. We have built models that explain, in broad strokes, how these objects work. But the fine details, the anomalies, the signals that do not quite fit, those are still piling up. And each one is a reminder that the universe is not obligated to make sense on our timeline. We will figure it out eventually, probably. But the process is slow, and the data is sparse, and the objects we are trying to understand are thousands of light years away, spinning hundreds of times per second, emitting radiation across the entire electromagnetic spectrum, and occasionally doing things we did not predict. Fast radio bursts are being detected at a rate of a few per day now. That is orders of magnitude more than a decade ago. The more we find, the more patterns we can extract. Repeaters versus non-repeaters. Nearby versus distant. High energy versus low energy. Each burst adds to the dataset. Each dataset narrows the range of possible explanations. We are closing in on the answer, slowly. The 22-minute signal has only been observed for a limited time. More observations are planned. More telescopes are being pointed at Gleam X. If the signal keeps repeating, if we can measure its properties in more detail, we will learn whether it is a neutron star or a white dwarf or something else. Geminga is being monitored continuously. The positron flux is being measured. The Pulsar Wind Nebula is being mapped. Every new observation refines the models. Every refined model makes better predictions. This is how science works. You find something weird. You try to explain it. The explanation does not quite fit. You refine it. You gather more data. Eventually, the pieces click into place, or they do not, and you have to start over with a new model. But while we are refining models and gathering data, neutron stars are out there doing their thing, spinning, beaming, flaring, producing antimatter, sending out bursts of radio waves we cannot yet explain. And occasionally, when two of them get too close, they spiral together, merge, and release a burst of gravitational radiation so powerful it ripples through the fabric of space-time itself. That is where we go next, because as strange as isolated neutron stars are, the ones in binary systems are stranger. And when they collide, they do not just make signals, they make elements, gold, platinum, the heaviest atoms in the periodic table, forged in the chaos of two dead stars tearing each other apart. That is the next chapter, ripples in space-time, the sound of two neutron stars screaming as they fall into each other, and what we learned the first time we managed to listen. We left off in a strange place. Neutron stars producing antimatter, radio bursts that repeat on no schedule, signals arriving every 22 minutes when nothing should be able to pulse that slowly and still light up the sky, objects that refuse to fit into the neat categories we built for them. And the whole time, while we were cataloguing these anomalies and refining our models and arguing over whether Gleam X was a neutron star or a white dwarf or something we did not have a name for yet, another kind of signal was sitting in the data, quiet, subtle, a whisper in the noise that nobody could hear until we built instruments sensitive enough to listen. not electromagnetic radiation, not light or radio waves or gamma rays, something deeper. Ripples in the fabric of space-time itself, gravitational waves. And when we finally detected them, when we finally proved they were real, and not just a mathematical curiosity buried in Einstein's equations, one of the first sources we found was a pair of neutron stars falling into each other, screaming as they died. Gravitational waves are not light. They are not particles. They are distortions in space-time, the four-dimensional fabric that everything in the universe sits on. Mass and energy curve space-time. That is what gravity is. The Earth orbits the Sun not because the Sun is pulling on it with some invisible force, but because the Sun's mass warps space-time around it, and the Earth is following the straightest possible path through that warped space. A marble rolling around the inside of a bowl. The marble is not being pulled, the bowl is curved. General relativity, Einstein's theory of gravity, predicts that when massive objects accelerate, they create waves in space-time that propagate outward at the speed of light, ripples. Like dropping a stone in a pond, except the pond is the universe, and the stone is a pair of neutron stars spiraling toward each other at a significant fraction of the speed of light. Einstein published the theory in 1915. He predicted gravitational waves almost immediately. Then he spent years second-guessing himself, publishing papers arguing they might not be real, then retracting those papers, then arguing again. The mathematics was clear. Accelerating masses should produce gravitational radiation, but the effect was so absurdly small that Einstein doubted it could ever be measured. He was almost right. Detecting gravitational waves required building the most sensitive measuring instruments ever constructed. Devices capable of detecting a change in distance smaller than the width of a proton across a baseline of several kilometers. That is the precision we're talking about. If you stretched a ruler from here to the nearest star 4 light-years away, and someone moved the far end by the width of a human hair, that is roughly the scale of distortion a gravitational wave creates as it passes through Earth. Detecting that requires lasers, mirrors, vacuum chambers, and a level of engineering that borders on the absurd. The first indirect evidence for gravitational waves came in the 1970s, from a binary pulsar system discovered by Russell Hulse and Joseph Taylor. The system, designated PSR-B 1913+16, consists of 2 neutron stars orbiting each other every 8 hours. One of them is a pulsar. It beams radio waves at Earth with every rotation, and because pulsars are extraordinarily precise clocks, Hulse and Taylor could measure the orbit with incredible accuracy. They tracked the system for years, and what they found was that the orbit was shrinking. The 2 neutron stars were spiraling closer together, not quickly. The orbital period was decreasing by about 76 microseconds per year. Tiny, but measurable, and the rate of decay matched almost perfectly the prediction from general relativity for how much energy the system should be losing to gravitational waves. The waves themselves were not detected, but the effect of the waves, the gradual loss of orbital energy, was exactly what Einstein's equations predicted. Hulse and Taylor won the Nobel Prize in 1993. The citation called it the first indirect evidence for gravitational radiation. Indirect because they did not detect the waves. They detected the consequence of the waves. The neutron stars were losing energy. That energy had to be going somewhere. Gravitational waves were the only explanation that fit. For decades, that was the state of the field. We knew gravitational waves existed because we could see their effect on binary pulsars, but we could not detect them directly. Building a detector sensitive enough to measure the passing of a gravitational wave required technology that did not exist in the 1970s. It took another 40 years of engineering, funding battles, and incremental improvements before the Laser Interferometer, Gravitational Wave Observatory, LIGO, came online. 2 detectors, one in Hanford, Washington, one in Livingston, Louisiana. Each one an L-shaped tunnel system 4 kilometers long, with mirrors at the ends and lasers bouncing back and forth thousands of times to measure the distance between the mirrors with absurd precision. When a gravitational wave passes through, space-time itself stretches and compresses. One arm of the L gets slightly longer, the other gets slightly shorter. The lasers detect the change. The signal is so faint that a single detector would drown in noise. Trucks driving past, earthquakes on the other side of the planet, ocean waves breaking on distant coasts. All of it shakes the ground enough to swamp the signal, but with two detectors separated by thousands of kilometers, you can cross-check. A real gravitational wave hits both detectors at slightly different times, because it takes a few milliseconds for the wave to travel from one site to the other. Noise does not correlate. The wave does. That is how you tell the difference. LIGO turned on in 2002, ran for several years, detected nothing, shut down for upgrades. Advanced LIGO came online in September 2015. Within days, it detected a signal, a gravitational wave from two black holes, each about 30 solar masses, colliding 1.3 billion light-years away. The signal lasted a fraction of a second. A chirp. The frequency rising as the black holes spiraled closer, moving faster, orbiting each other dozens of times in the final moments before they merged. Then silence. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that same moment. For a brief instant, the merger was the loudest thing in the universe. Not in sound, not in light, in space-time itself. The announcement came in February 2016 and it changed physics. Gravitational waves were no longer theoretical. They were detected, measured, analysed. The era of gravitational wave astronomy had begun. Over the next 2 years, LIGO and its European counterpart Virgo detected more black hole mergers, 10, then 20. Each one a collision between objects so massive and so compact that the only way to observe them was through the ripples they left in space-time. No light, no electromagnetic signal, just the gravitational wave chirp. A clean, elegant signal that matched the predictions from general relativity so precisely it was almost eerie. The models worked. The detectors worked. Everything Einstein said would happen was happening exactly the way he said it would. Then, in August 2017, the detectors picked up something different. A longer signal, 100 seconds instead of a fraction of a second. The frequency was lower, the amplitude smaller, but the pattern was unmistakable. Two objects spiraling together, merging. This time, the masses were wrong for black holes. Too light. About 1.4 solar masses each. Neutron stars. The event was designated GW170817, named for the date it was detected. August 17, 2017. The gravitational wave signal told the story. Two neutron stars, each about 1.4 times the mass of the Sun, had been orbiting each other for billions of years. The orbit had been decaying the entire time, losing energy to gravitational waves, spiraling closer, faster. By the time LIGO and Virgo detected them, the two stars were orbiting each other hundreds of times per second, separated by only a few hundred kilometers. Close enough that tidal forces were starting to distort their shapes. Each star was pulling on the other, stretching it into an elongated shape, a football instead of a sphere. The tidal distortion changes the gravitational wave signal. It makes the waveform more complicated. And by analysing that complication, physicists could infer properties of the neutron stars themselves. How stiff they were, how much they resisted being squeezed, the equation of state, that term again, the relationship between pressure and density for matter at nuclear densities, the thing we still do not fully understand. GW170817 gave us the best measurement of the neutron star equation of state we have ever had. Not perfect, not complete, but better than anything we could get from observing isolated neutron stars. The gravitational wave signal lasted 100 seconds. Then it cut off. The two neutron stars had merged. What happened next depended on the total mass of the system. If the combined mass was below a certain threshold, about 2.5 solar masses give or take, the result would be a single, more massive neutron star, heavier than either of the originals, but still supported by neutron degeneracy pressure. If the mass was above the threshold, the merged object would be too heavy. Neutron degeneracy pressure would fail. The object would collapse into a black hole. GW170817 was right at the edge. The combined mass was roughly 2.7 solar masses, close enough to the limit that it was unclear what the remnant would be. A very heavy neutron star, possibly unstable, possibly collapsing into a black hole after a few seconds or minutes, or an immediate collapse. The gravitational wave signal alone could not tell us. The wave stopped when the merger happened because the system stopped changing. Either it became a single object, spinning rapidly and settling down, or it became a black hole and there was nothing left to radiate. To know which, you needed to see what happened afterward. and for that, you needed light. 2 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a burst of gamma rays from the same region of sky. A short gamma ray burst, the kind astronomers had been seeing for decades without fully understanding their origin. Short gamma ray bursts last less than 2 seconds. They are different from long gamma ray bursts, which last more than 2 seconds and are associated with supernova explosions. Short bursts were always mysterious. Too brief to be supernovae, too energetic to be anything ordinary. The leading theory was that they came from neutron star mergers, but nobody had direct proof. GW170817 was the proof. The gamma ray burst arrived 2 seconds after the gravitational waves, close enough in time and space that the association was undeniable. The merger had produced a jet, a narrow beam of relativistic particles and radiation shot out along the rotation axis of the merged object, powered by the energy of the collision. The jet happened to be pointed roughly in our direction, not directly at us, or the gamma ray burst would have been much brighter, but close enough that we caught the edge of the beam. That was the gamma ray burst. Confirmation that short gamma ray bursts are in fact produced by neutron star mergers, a mystery solved. But the gamma rays were just the beginning. Within hours, telescopes around the world swung toward the source location. Optical telescopes, infrared, radio, X-ray, every wavelength we could observe. And they all saw the same thing. A new point of light in a galaxy called NGC 4993, about 130 million light-years away in the constellation Hydra. The light was bright in the first few hours. Blue. Then it faded over the next few days, shifting toward red. The spectrum showed features that had never been seen before in any astronomical transient. Heavy elements, lots of them. The light curve, the way the brightness changed over time, matched the predictions for a kilonova. A radioactive afterglow powered by the decay of freshly synthesized heavy nuclei. This was not a supernova. Supernovae are powered by the shockwave from a collapsing star. Kilonovae are powered by something else, neutron capture, the rapid capture of neutrons by atomic nuclei in the debris of a neutron star merger, building up heavier and heavier elements in a process that only works when you have an absurd density of free neutrons, which is exactly what you get when you shred 2 neutron stars and scatter their guts into space. Let's talk about how elements are made. The Big Bang produced hydrogen, helium, and traces of lithium. That is it. Everything else, every element heavier than lithium, was made inside stars or in the explosions that destroy stars. Normal fusion, the kind that powers the sun, builds elements up to iron. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, on up the periodic table. But fusion stops at iron because fusing iron costs energy instead of releasing it. Iron is the most stable nucleus. You cannot get energy out of it by fusing it into something heavier. So elements heavier than iron have to be made a different way. And the main way is neutron capture. If you bombard a nucleus with neutrons, some of those neutrons will stick. The nucleus gets heavier. Eventually, one of the neutrons decays into a proton, and the element changes. You have transmuted one element into another. This process happens in 2 flavors. Slow neutron capture, called the IS process, happens inside certain types of stars over thousands of years. The neutron flux is low, nuclei capture neutrons one at a time with long gaps in between. This process builds up elements gradually. It is responsible for about half the elements heavier than iron. The other half comes from rapid neutron capture, the R process. Rapid means the neutron flux is so high that nuclei capture dozens of neutrons in a fraction of a second before any of them have time to decay. This only happens in environments where the density of free neutrons is absurdly high, and for decades, the only place we knew of that could do that was a supernova explosion, specifically the neutrino-driven wind from a collapsing stellar core. The problem was, when astrophysicists ran the simulations, the numbers did not quite work. Supernovae did produce some R-process elements, but not enough. The amount of gold and platinum and uranium we see in the universe is higher than supernovae can account for. Something else had to be making those elements, and the something else, it turns out, is neutron star mergers. When 2 neutron stars collide, they do not merge cleanly. The collision is violent. Tidal forces rip the stars apart. Material from the outer layers gets flung into space, not the cores. The cores merge or collapse into a black hole. but the outer layers, the crusts, the neutron-rich material that was sitting just below the surface that gets ejected. And that material is almost pure neutrons, free neutrons, unbound, drifting through space, decaying into protons on a timescale of about 10 minutes. But before they decay, they can be captured by any nuclei in the vicinity. And there are a lot of nuclei in the vicinity, because the ejected material is not entirely neutrons. It contains some iron, some lighter elements, seed nuclei. Those seed nuclei start capturing neutrons, rapidly, dozens per nucleus. The nuclei get heavier and heavier, climbing up the periodic table, building elements that do not exist anywhere else. Gold, platinum, uranium, all the heavier stable and unstable elements. The R process runs for a few seconds, then the neutron supply runs out. The newly formed heavy nuclei are radioactive. They decay, releasing energy in the form of heat and light. That is the kilonova, a glowing cloud of freshly synthesized heavy elements expanding into space, shining for a few days before fading into the background. The kilonova from GW 170817 was the first one ever observed in detail. The light curve matched the theoretical predictions almost perfectly. The spectrum showed clear signatures of heavy elements, exactly the elements you would expect from R-process nucleosynthesis. And by measuring the total amount of light emitted and comparing it to the models, astronomers estimated that the merger produced roughly 10 Earth masses of heavy elements. 10 Earths worth of gold, platinum and uranium, scattered into space in a single event. That is where those elements come from. Not from supernovae, or at least not mostly from supernovae, from neutron star mergers. Every gold ring, every platinum catalyst, every uranium fuel rod was forged in the collision of two dead stars billions of years ago. The atoms in those objects drifted through space, mixed with the interstellar medium, condensed into a new generation of stars and planets, and eventually ended up here, in jewelry, in electronics, in nuclear reactors. The universe recycles. And neutron star mergers are one of the recycling plants. GW 170817 was a watershed moment, not just because it was the first neutron star merger detected in gravitational waves, not just because it confirmed that short gamma-ray bursts come from neutron star mergers, not just because it proved colonovae are real and R-process nucleosynthesis happens in mergers. All of that was huge, but the bigger deal was that it was the first multi-messenger astronomy event involving gravitational waves. Multi-messenger means observing the same event in multiple types of signals, gravitational waves and light, two completely independent channels. Before GW 170817, gravitational wave detections were blind. LIGO and Virgo could tell you that two black holes collided, and they could tell you roughly where in the sky the event happened, but the error box was large. Hundreds of square degrees. You could not point a telescope at the source and see anything because black holes do not emit light. Neutron stars do, or at least the debris from their collisions does. GW 170817 was detected in gravitational waves, localized to a patch of sky, and then observed in gamma rays, X-rays, optical, infrared and radio within hours. Dozens of telescopes, hundreds of astronomers, all looking at the same event. That had never happened before, and what it proved was that gravitational wave astronomy is not just a new way to observe the universe, it is a new sense, like adding hearing to a creature that could only see. You learn things you could not learn with either sense alone. The detection also refined our understanding of the neutron star equation of state. When two neutron stars spiral together, the way they deform under tidal forces depends on how stiff they are. Stiff matter resists deformation. Soft matter deforms easily. The gravitational wave signal encodes that information in the waveform. By analysing the signal from GW 170817, physicists were able to constrain the equation of state more tightly than any previous observation. The result ruled out some of the more extreme models. Neutron stars are not as soft as some theories predicted. They are not as stiff as others predicted. They are somewhere in the middle. That narrows the range of possibilities for what is happening in the core. It does not tell us definitively whether quark matter exists or whether hyperons are present, but it eliminates some options, and every constraint helps. Since GW 170817, LIGO and Virgo have detected more neutron star mergers. Not many. Neutron star mergers are rarer than black hole mergers because neutron stars are less common and their orbits take longer to decay. Black holes are heavier, so they radiate gravitational waves more efficiently and spiral in faster. Neutron stars take longer, but they happen. And each new detection adds to the dataset. Each one gives us another measurement of the equation of state, another kilonova, another batch of our process elements scattered into space. Over the next decade, as the detectors get more sensitive and the observation time increases, we expect to detect neutron star mergers at a rate of a few per year, maybe more. Each one will teach us something about neutron stars, about nuclear matter, about how the heaviest elements in the universe are made, and about how space-time itself behaves when two of the densest objects in existence collide at a significant fraction of the speed of light. But LIGO and Virgo are not the only gravitational wave detectors. They are the only ones detecting high-frequency gravitational waves from stellar mass objects, black holes and neutron stars in the final moments before merger. The waves from those events have frequencies in the range of tens to thousands of hertz. Audible frequencies. You could, in principle, play the gravitational wave signal from a black hole merger through a speaker and hear it as a chirp, a rising tone that sweeps upward and cuts off abruptly. That is what LIGO hears. But gravitational waves come in other frequencies, lower frequencies, much lower, and to detect those you need a different kind of detector, one that is not built on Earth, one that uses the entire galaxy as an instrument. Pulsar timing arrays are networks of radio telescopes monitoring dozens of millisecond pulses simultaneously. Millisecond pulses are extraordinarily precise clocks. They tick with a regularity that rivals the best atomic clocks humans have built. By monitoring the arrival times of pulsar signals over years or decades, astronomers can detect tiny deviations in the timing, and one of the things that can cause a timing deviation is a gravitational wave passing between Earth and the pulsar. When a gravitational wave passes through, it stretches and compresses space-time. The distance between Earth and the pulsar changes very slightly. The pulsar is still ticking at the same rate, but the light from the pulsar has to travel a slightly different distance to reach us. That changes the arrival time. The effect is tiny, nanoseconds, but millisecond pulsars are precise enough that nanoseconds matter. The North American Nanohertz Observatory for Gravitational Waves, NanoGrav, is a collaboration monitoring more than 40 pulsars using radio telescopes across North America. Nanohertz means the gravitational waves they are looking for have frequencies around 1/1000th of a hertz. That corresponds to waves with periods of years to decades. Waves that oscillate so slowly you would have to monitor pulsars for a decade or more to see a single cycle. What produces gravitational waves at those frequencies? Not stellar mass objects. Those merge too quickly. The gravitational waves they produce are high frequency. Low frequency gravitational waves come from much more massive objects. Supermassive black holes, the kind that sit at the centers of galaxies, millions to billions of times the mass of the Sun. When two galaxies merge, their central black holes eventually sink to the center of the merged galaxy and begin orbiting each other. The orbit takes millions of years to decay, and during that time, the binary supermassive black hole radiates gravitational waves at nanohertz frequencies. One binary produces a faint signal, but there are millions of galaxies in the observable universe, millions of supermassive black hole binaries at various stages of inspiral, all of them radiating gravitational waves, all of those waves overlapping to create a background hum, a gravitational wave background. In June 2023, NanoGrav announced that they had detected the gravitational wave background. Not a single source, not a resolved binary, a diffuse hum in the data present in the timing residuals of all the pulsars they were monitoring. With the frequency spectrum and spatial correlation pattern expected from a stochastic background of gravitational waves produced by a cosmological population of supermassive black hole binaries. This was not the first detection of gravitational waves from a neutron star merger. It was not even a direct detection of a specific source. It was a detection of the combined signal from thousands or millions of black hole binaries across the universe, all radiating at once, creating a background noise in space-time itself. The announcement was huge. It confirmed that supermassive black hole binaries are common. It confirmed that pulsar timing arrays work as gravitational wave detectors, and it opened up a new window on the universe. LIGO and Virgo see stellar mass mergers. NanoGrav sees supermassive black hole binaries. Different objects, different frequencies, different science. Together they cover a vast range of the gravitational wave spectrum. The nanograv result does not directly tell us about neutron stars. Supermassive black holes are not neutron stars. They are millions of times heavier. But the detection matters because it shows that gravitational wave astronomy is not limited to one type of source or one frequency range. Space-time ripples at all scales, from stellar mass objects merging in fractions of a second to supermassive black holes spiraling together over millions of years. And by detecting both ends of the spectrum, we are learning that the universe is full of these events. Collisions, mergers, binaries losing energy and spiraling inward. It is happening everywhere, all the time, at every mass scale. Neutron stars colliding, black holes colliding, supermassive black holes colliding. The universe is a violent place, and gravitational waves are how we hear the violence. The comparison between LIGO and nanograv is worth pausing on, because it illustrates how much we have learned in the last decade. LIGO detects a single merger event, two neutron stars colliding 130 million light-years away. The signal lasts 100 seconds. We analyse the waveform, extract the masses and spins and tidal deformations, match it to an optical counterpart, observe the kilonova, and learn about nuclear physics and element formation. That is precision science. One event, studied in exhaustive detail. Nanograv detects a background, thousands or millions of supermassive black hole binaries spread across the universe, all radiating at once. We cannot resolve individual sources yet. We do not know which galaxies the binaries are in. We just know the background is there. That is statistical science. A large population studied in aggregate. Both approaches are valuable. Both teach us things the other cannot. And together, they are building a complete picture of how compact objects behave across the entire mass range and across the entire history of the universe. Gravitational wave detections also test general relativity in regimes we could not access before. Einstein's theory has been tested extensively in weak gravitational fields, the orbits of planets, the bending of light around the Sun, the precession of Mercury's orbit. All of those tests confirmed that general relativity works. But they are weak field tests. The gravitational fields involved are tiny compared to what exists near a neutron star or a black hole. Strong field tests require observing objects where gravity is so strong it dominates everything else. Neutron stars are strong field objects, black holes are strong field objects, and when two of them collide, the gravitational field becomes as strong as it can possibly get without forming a singularity. The waves produced by those collisions carry information about how gravity behaves in that regime, and so far every gravitational wave detection has matched the predictions of general relativity. The waveforms look exactly like the models say they should. The frequency evolution, the amplitude, the ring down after the merger, all of it fits. There is no deviation, no sign that general relativity breaks down at strong field. That is remarkable. The theory is over 100 years old. It was written by one person using pen and paper, and it still works, even in the most extreme environments the universe has to offer. But tests are not finished. There are alternative theories of gravity, modifications to general relativity that predict slightly different waveforms, slightly different propagation speeds for gravitational waves, slightly different amounts of energy radiated. Each new detection gives us another chance to test those alternatives. So far, none of them fit the data as well as general relativity does, but we keep testing, because if general relativity does break down somewhere, the place it is most likely to break down is in the strong field, near a neutron star, near a black hole, during a merger. And when we find the deviation, if we find it, it will be one of the most important discoveries in the history of physics, a hint that there is something deeper than general relativity, some more fundamental theory waiting to be uncovered. For now, Einstein is still winning. Let's come back to the question of what happens during a neutron star merger, because the details matter, and they are stranger than the summary suggests. Two neutron stars orbit each other. The orbit decays, they spiral closer. At some point, they get close enough that tidal forces start to matter. Each star raises a tidal bulge on the other. The bulge is not symmetric. It lags behind the orbit because the star's structure cannot respond instantaneously. That lag transfers energy. The orbit decays faster. The stars spiral in faster. Tidal forces get stronger. The bulges get bigger. There is a feedback loop. As the stars get closer, the tidal distortion increases, which increases the energy loss, which brings the stars closer faster. By the time the stars are a few hundred kilometers apart, They are orbiting each other hundreds of times per second, and the tidal bulges are enormous. The stars are no longer spheres, they are elongated, egg-shaped, stretching toward each other, then they touch. Not a gentle contact, a collision at relativistic speeds. The outer layers of both stars are ripped off and flung into space. The cores merge. If the total mass is below the limit, the merged core becomes a massive neutron star. It is hot, spinning rapidly, possibly 1,000 times per second, unstable. The star has too much angular momentum and too much thermal energy. It cannot settle into a stable configuration immediately. It rings, oscillates, radiates gravitational waves. Over the course of seconds or minutes, it loses energy, slows down, cools slightly, settles into a new equilibrium, a hypermassive neutron star, heavier than any stable neutron star, but held up temporarily by rotation and thermal pressure. Eventually, as it continues to cool and spin down, it will cross the stability threshold and collapse into a black hole. That collapse could happen seconds after the merger, or minutes, or hours. We do not know. The gravitational wave signal cuts off when the stars merge because the dynamics change. The post-merger signal is much weaker and at higher frequencies. LIGO is not sensitive enough to detect it clearly. Yet, if the total mass is above the limit, the collapse happens immediately. The cores merge. The combined mass is too great. Neutron degeneracy pressure fails. The object collapses into a black hole in less than a second. The event horizon forms. Everything inside is cut off from the outside universe. The only things that escape are gravitational waves from the final moments before the horizon forms and the electromagnetic radiation from the debris flung into space during the collision. The gamma ray burst. The kilonova. All of that comes from material that was ejected before the black hole formed. Once the horizon is there, nothing else gets out. The black hole sits there spinning, surrounded by a cloud of hot debris, and slowly it swallows the debris over the next few hours or days. By the time the kilonova fades, the system is dark. A black hole, alone, heavier than the two neutron stars that formed it, and sitting in a region of space now enriched with 10 Earth masses of heavy elements that were not there a week earlier. The fact that we can observe all of this, that we can detect the gravitational waves, see the gamma ray burst, watch the kilonova evolve, and measure the spectrum of the ejector, is extraordinary. We are watching the universe build the periodic table in real time. Every element heavier than iron in your body, in the ground, in the devices around you, came from events like this: neutron star mergers, or supernovae, for about half of them. But the heaviest elements, the ones at the bottom of the periodic table, the ones that do not get made in supernovae, those came from mergers. And we have now seen it happen. Not inferred it from models, seen it. The light curve matches, the spectrum matches, the gravitational wave signal matches, everything fits. This is not speculation, this is observation, and the observations are only going to get better. LIGO and Virgo are being upgraded. The next observing run will be more sensitive. Japan is building a detector called Kagra. India is planning one. Eventually there will be a network of gravitational wave detectors spread across the globe, all operating simultaneously, cross-checking signals, triangulating sources with much higher precision than 2 or 3 detectors can achieve. Each new detector improves the localization, makes it easier to point optical telescopes at the right patch of sky, easier to catch the kilonova in the first few hours when it's brightest, easier to measure the spectrum and learn about the elements being produced. And in space, the European Space Agency is planning the Laser Interferometer Space Antenna, LISA, a constellation of 3 satellites flying in formation, separated by millions of kilometers, using lasers to measure the distance between them with absurd precision. LISA will detect gravitational waves at frequencies between LIGO and nanograv. Millihertz frequencies, waves from intermediate mass black hole binaries, stellar mass black holes spiraling into supermassive black holes, white dwarf binaries, maybe even exotic sources we have not predicted. LISA is not scheduled to launch until the mid-2030s, but when it does, it will open yet another window on the gravitational wave spectrum, so where does that leave us? We started this chapter talking about binary neutron stars, 2 dead stars orbiting each other, losing energy to gravitational waves spiraling inward over billions of years until they collide. We talked about the merger, the kilonova, the production of heavy elements, the gravitational wave signal and what it tells us about the equation of state of nuclear matter. We talked about GW 170817, the first multi-messenger event, and how it confirmed decades of theory about short gamma-ray bursts and R-process nucleosynthesis. We talked about nanograv detecting the gravitational wave background from supermassive black hole binaries, proving that the universe is full of these violent events at every scale. And we talked about the future. More detectors, more sensitivity, more events. The field is young. Gravitational wave astronomy is barely a decade old. We have detected a few dozen events, a handful of neutron star mergers. The next decade will bring hundreds, maybe thousands, each one a new data point, each one refining our models, each one teaching us something about how matter behaves at the edge of stability. But gravitational waves are not the only thing neutron stars produce when they die, because while we were studying mergers and color novae and gravitational wave signals, another category of explosions started showing up in the data: bright, brief, energetic, and completely unexplained by any model we had. These were not supernovae, not gamma-ray bursts, not kilonovae. They were something else, something faster and stranger. And when astronomers tried to figure out what was producing them, the answers kept pointing back to neutron stars, or at least to something involving neutron stars doing things we did not predict. Those explosions and what they might be telling us about the most extreme events in the universe are where we go next. We left off watching space-time itself ripple, two neutron stars spiraling together, radiating gravitational waves, colliding in a flash of gamma rays and a slow, glowing cloud of freshly forged heavy elements. A kilonova, the first multi-messenger event, proof that the heaviest atoms in the universe are made when dead stars tear each other apart. We talked about how LIGO and Virgo detected the merger, how telescopes around the world swung toward the source within hours, how the light curve matched the predictions, how the spectrum showed gold and platinum scattered into space. Everything fit. The models worked. The observations confirmed decades of theory. For a brief moment, it felt like we understood what happens when neutron stars collide. Then, as the universe tends to do just when we think we have things figured out, something else showed up in the data. Something brighter, something faster, something that made no sense. In June 2018, a survey telescope in Hawaii detected a new point of light in a galaxy about 200 million light-years away. The object was designated at 2018 Cow. The name is automatic, AT for astronomical transient, 2018 for the year. Cow because the naming system cycles through 3-letter combinations and it happened to land on COW. Normally these designations are boring, strings of letters and numbers that tell you when something was discovered and nothing about what it is. This one was different. Astronomers started calling it the Cow, not because the name was funny, though it was, because the object itself was so strange that a memorable nickname helped keep track of it in a field where dozens of transients are discovered every night. The Cow was bright. Absurdly bright. Within 2 days of detection, it had reached peak luminosity, outshining the entire galaxy it was sitting in. That alone was unusual. Supernovae take weeks to reach peak brightness. This thing peaked in 2 days, then it started fading, fast. Within 2 weeks, it had dropped by a factor of 10 in brightness. Supernovae fade slowly, over months. The Cow faded in weeks. The light curve, the graph of brightness over time, was steeper than anything in the standard catalogues. Astronomers who study transients, exploding stars and other temporary bright objects, have seen thousands of supernovae. They know what a normal supernova light curve looks like: slow rise, broad peak, gradual decline. The Cow did not look like that. It looked like someone had turned on a cosmic floodlight, left it on for a few days and then flipped the switch off. The spectrum was wrong too. Most supernovae are red or yellowish. The light comes from a hot expanding shell of gas, and the temperature of that gas determines the colour. A typical supernova shell is a few thousand degrees, hot by human standards, cool by astrophysical standards. The Cow was blue, deep blue. The kind of blue you only get from something extremely hot, tens of thousands of degrees, maybe more. The spectrum showed broad emission lines, which meant the material was moving fast, expanding at thousands of kilometers per second. That part was normal for an explosion. but the combination of extreme brightness, rapid evolution, and high temperature did not fit any known type of supernova. It was not a Type C, not a Type 2, not a superluminous supernova. It was something else. Within days of the discovery, telescopes across the electromagnetic spectrum started observing the cow. Optical telescopes tracked the light curve. Radio telescopes detected synchrotron emission, the kind of radiation you get when electrons are accelerated to relativistic speeds in a magnetic field. X-ray telescopes saw high-energy emission from the center of the explosion. The object was radiating across the entire spectrum, and the more data came in, the stranger it looked. The radio emission peaked weeks after the optical peak, which suggested there was a shockwave plowing through surrounding material. The X-ray emission was variable, flickering on timescales of hours to days, which suggested something compact and energetic was sitting at the center. Compact objects do not just mean small. In astrophysics, compact means dense. Neutron stars, black holes, things with gravitational fields strong enough to dominate the dynamics. The leading theory, and it is still just a theory, is that the cow was a star collapsing into a black hole, or a neutron star, and the collapse produced a relativistic jet. A narrow beam of particles moving at nearly the speed of light, blasting out from the poles of the collapsing core. Jets are not uncommon in astrophysics. We see them in gamma-ray bursts. We see them in active galactic nuclei where supermassive black holes are feeding. The mechanism is well understood in broad strokes. Material falls toward a compact object, gets heated, gets funneled along magnetic field lines, and accelerates. If the magnetic field is strong enough and the accretion rate is high enough, the jet can reach relativistic speeds. The jet punches through the surrounding material, and when it breaks out into open space, it produces a bright flash of radiation. If the jet happens to be pointed toward us, we see the full brightness. If it is pointed away, we see nothing. Jets are directional. Lighthouses again. The cow, the theory goes, was a jet pointed roughly in our direction. Not directly at us, or it would have been even brighter, but close enough that we caught a good view. The problem with the jet model is that it requires a central engine, something to power the jet, something compact, a newly formed neutron star or a black hole. If the cow was a supernova, the core should have collapsed into one or the other, but the light curve was too fast. Normal supernovae are powered by radioactive decay. Nickel-56 decays into cobalt-56, which decays into iron-56, and each decay releases gamma rays that heat the expanding shell. The heating is what makes the supernova glow. The process takes weeks to peak and months to fade because radioactive decay does not happen instantly. The cow peaked in 2 days. Radioactive decay cannot explain that. Something else was pumping energy into the system. Fast. The best candidate is a central engine. A neutron star spinning hundreds of times per second, pouring rotational energy into the surrounding material. Or a black hole accreting material at a furious rate, converting gravitational potential energy into radiation. Either one could explain the rapid evolution. Either one could power a jet. But here is the thing. If the cow was a collapsing star forming a neutron star or a black hole, we should have detected a neutrino burst. Core collapse supernovae emit enormous numbers of neutrinos when the core collapses. Neutrinos are nearly massless particles that barely interact with matter. They pass through the Earth as if it were not there. But if you have a sensitive enough detector, you can catch a few of them. Neutrino detectors around the world are constantly monitoring for these bursts. When supernova 1987A exploded in the Large Magellanic Cloud, a galaxy about 160,000 light-years away, detectors in Japan, the United States and Russia detected a burst of about 24 neutrinos arriving hours before the light from the explosion. That was proof the core had collapsed. The neutrinos escaped first because they do not interact with the surrounding material. The light had to fight its way out through the expanding shell. The cow did not produce a detected neutrino burst. That does not mean there was not one. The cow was much farther away than supernova 1987A, 200 million light-years versus 160,000. The neutrino flux drops off with the square of the distance. A supernova at that distance would produce a much weaker signal, maybe too weak for our current detectors to pick up. Or maybe the cow was not a normal core collapse. Maybe the central engine formed through a different process. A merger, a direct collapse, something exotic. The cow was not alone. Once astronomers knew what to look for, they started finding more. Similar events, bright, fast blue transients that did not fit the supernova template. The class got a name: Luminous Fast Blue Optical Transients, LF-BOTS, pronounced LF-BOTS by some, LFBOTS by others, depending on who you ask. The name is descriptive: luminous because they are extremely bright, fast because they evolve quickly, blue because their spectra peak in the blue part of the visible spectrum or even in the ultraviolet, optical because they are detected primarily in visible light, though they also emit in other wavelengths, transient because they do not last. They flare up, shine for a few days or weeks, and fade. By the time you write a proposal to observe one with a major telescope, it is already gone. Since the cow, astronomers have found a handful of other LF-BOTS, not many, maybe a dozen confirmed cases as of the last few years. That's a tiny sample, too small to draw firm conclusions, but patterns are starting to emerge. Most LF-BOTS are found in star-forming galaxies with lots of young, massive stars. That suggests the events are connected to massive stars dying, not a surprise. Most cosmic explosions come from massive stars, but the host galaxies are not always typical. Some LF-BOTS have been found in the outskirts of their host galaxies, far from the central regions where most star formation happens. A few have been found in between galaxies, in the intergalactic medium. That is strange. Stars do not usually form in those regions. If the LF-BOT progenitor is a massive star, how did it get there? Maybe it was ejected, kicked out of the galaxy by a supernova explosion or a gravitational interaction. Massive stars can be ejected if they are in a binary system, and their companion explodes asymmetrically. The explosion kicks both stars. One might end up drifting into intergalactic space. Millions of years later, it explodes, an LF-BOT in the void. Another possibility is that LF-BOTs are not single stars at all. They could be mergers, not neutron star mergers like GW170817, something different. A neutron star merging with a black hole, or a neutron star merging with a normal star, or a white dwarf merging with something. Mergers are violent. They release enormous amounts of energy in short timescales. They can produce jets. They can happen anywhere. If a neutron star in a binary system spirals into a black hole, the neutron star gets torn apart by tidal forces before it crosses the event horizon. The debris forms an accretion disk around the black hole. The disk is hot, dense, and rotating rapidly. Under the right conditions, it can launch a jet. The jet punches through any surrounding material and produces a bright transient, an LF-BOT. This model explains the rapid evolution. It explains the high luminosity. It explains the blue color. And it explains why some LF-BOTs are found in strange locations. Mergers can happen anywhere a binary system ends up, and binaries can be flung into intergalactic space by gravitational interactions. The problem with the merger model is that it does not explain all the data. Some LF-BOTs show spectral features that look like supernova ejecta, hydrogen, helium, oxygen, elements you would expect if a star exploded. Mergers do not necessarily produce that kind of ejecta. A neutron star merging with a black hole would shred the neutron star, but the debris would be mostly neutron-rich material, heavy elements, not the lighter elements seen in some LF-BOT spectra. So maybe LF-BOTs are not a single class of events. Maybe the name is an umbrella covering multiple types of explosions that happen to look similar in optical light but have different physical origins. Fast blue transients from jets produced by newborn neutron stars. Fast blue transients from neutron star black hole mergers. Fast blue transients from something else we have not thought of yet. The field is too young, and the sample size too small to say for sure. One of the key observations that could settle the question is whether LF-BOTs produce gravitational waves. If an LF-BOT is a merger, neutron star and black hole, or neutron star and neutron star, the inspiral should radiate gravitational waves. LIGO and Virgo should detect it. If they do not, either the event is not a merger, or the merger happened too far away for the detectors to pick up the signal. The challenge is timing. Gravitational wave detectors do not scan the entire sky continuously. They listen. When they detect a signal, they send out an alert with a rough location. Then optical telescopes follow up, but LF-BOTs are discovered by optical surveys. The transient appears in the images. Astronomers notice it. They start follow-up observations. By that time, if there was a gravitational wave signal, it has already come and gone. The only way to make the connection is if an LF-BOT happens to occur while LIGO and Virgo are observing, and the gravitational wave signal is strong enough to detect and the location matches. That has not happened yet. But the detectors are getting more sensitive. The optical surveys are finding more transients. Eventually, if LF bots do come from mergers, we will catch one in the act. Let's talk about jets because they keep showing up in the models and they are worth understanding. A relativistic jet is not a stream of gas. It is a beam of plasma, ionized particles, mostly electrons and protons, moving at speeds very close to the speed of light. 99% the speed of light. 99.9%. At those speeds, special relativity kicks in. Time dilation, length contraction. The particles in the jet are so energetic that their mass effectively increases. A proton moving at 99.9%, the speed of light has about 22 times its rest mass. The kinetic energy is absurd, and when that jet slams into surrounding material, stationary gas or dust, or the outer layers of a star, the collision is violent. The particles in the jet collide with the particles in the material. The collisions produce shocks. The shocks heat the material to millions of degrees. The heated material radiates X-rays, gamma rays, optical light. The jet does not just plow through, it interacts, and the interaction is what makes the transient visible. The energy in a relativistic jet can exceed the energy output of an entire galaxy. Not for long. Jets last seconds to minutes in gamma-ray bursts, days to weeks in LF bots. But during that time, the jet is one of the brightest things in the universe. The energy comes from the central engine, a black hole or a neutron star. If it is a black hole, the energy comes from accretion, material falling in, heating up, releasing gravitational potential energy. If it is a neutron star, the energy comes from rotation. A newly formed neutron star can spin hundreds of times per second. The rotational energy is enormous. As the star spins down, it transfers energy to the surrounding material through magnetic fields. The fields accelerate particles. The particles form a jet. Over time, the star slows down, the energy output drops, and the jet fades. That timescale, seconds to weeks, matches the timescale of LF bots, which is why newly formed neutron stars, sometimes called millisecond magnetars in this context, are one of the leading candidates for the central engine. The term magnetar shows up again because the magnetic field matters. A normal neutron star has a magnetic field around 1 trillion Gauss. A magnetar has a field around 1 quadrillion Gauss. If you form a neutron star with an unusually strong magnetic field, the field can dominate the dynamics. It can channel the outflow into jets. It can accelerate particles to relativistic speeds, and it can transfer rotational energy to the surrounding material much faster than a normal pulsar would. A millisecond magnetar spinning hundreds of times per second with 1 quadrillion Gauss magnetic field could power an LF bot. The star forms. The magnetic field spins with it. The field drags charged particles around. The particles radiate. The radiation escapes. We see a bright, fast blue transient. Then the star spins down. The magnetic field decays slightly. The emission drops. The transient fades. Over a few weeks, the Magnetar goes from newborn monster to just another neutron star sitting in a supernova remnant. By the time the remnant is old enough to be interesting to other astronomers, the Magnetar phase is over. It is just a pulsar, or not even that. It could be a quiet neutron star, spinning slowly, no longer beaming in our direction. Invisible. There is another angle to this. If LF bots are powered by jets, and jets are directional, then for every LF bot we see, there should be many more pointing away from us. The jet has to be aimed roughly in our direction for us to catch the full brightness. If it is aimed elsewhere, we either see a much fainter transient, or we see nothing at all. This is the beaming problem. It shows up in gamma-ray burst studies too. We know gamma-ray bursts are jetted because we see asymmetries in the light curves, and because the total energy would be absurd if the emission were isotropic. If a gamma-ray burst radiated equally in all directions, some of them would be releasing more energy than a supernova by factors of 100 or 1,000. That does not make sense. The energy budget is too high. But if the emission is concentrated into a narrow jet, the total energy is much lower. Only the material in the jet is moving relativistically. The rest of the explosion is slower, fainter, not visible, unless you are looking from the right angle. LF bots might work the same way. Every LF bot we detect could represent 10 or 100 similar events that happened but were not aimed at us. That would mean the true rate of these explosions is much higher than the detection rate suggests, which would mean they are not as rare as they seem, just hard to see unless you get lucky. Now let's talk about the unseen phenomena, because LF bots are strange, but they are at least detected. We see them, we measure their light curves, we take spectra, we argue about what they are. There is data, but there is a broader question lurking in the background. What else is out there that we are not seeing? Transients are by definition temporary, they flare up and fade. If you're not looking at the right part of the sky at the right time, you miss them. Survey telescopes help. Wide-field cameras that image large sections of the sky every night, comparing new images to old ones, looking for anything that has changed. A new point of light, a star that got brighter, a galaxy that suddenly has a bright spot in it. These surveys have revolutionized transient astronomy. Before surveys, we found supernovae by accident or by painstaking manual searches. Now we find dozens per night. But surveys have limits. They have a detection threshold. Faint objects do not trigger alerts. They have cadence limits. If a transient flares up and fades in less than a day, and the survey only images that part of the sky once every few days, you miss it. And they have wavelength limits. Optical surveys see optical transients. They do not see radio transients unless someone follows up. They do not see X-ray transients unless a space telescope happens to be looking. There could be entire classes of transients we have never detected, because they happen in wavelengths we do not monitor, or on timescales we do not sample. Fast radio bursts were invisible until we had radio telescopes with the right combination of sensitivity, time resolution, and sky coverage. Before that, they were happening all the time, thousands per day across the entire sky. We just were not listening. LF bots might be similar. We only started noticing them after surveys got sensitive enough and fast enough. Before that, they were probably happening, flaring up, fading, gone before anyone could point a telescope at them. Now that we know they exist, we're finding more. Each new one refines the light curve template, refines the colour, refines the expected brightness, and that makes it easier to find the next one. But there are hints of other things. Brief flashes in old survey data that were dismissed as artifacts at the time but might have been real. Transients that peaked and faded within hours. Too fast for radioactive decay. Too fast for normal supernova models. No follow-up because the alerts came too late. By the time anyone could observe the location, the transient was gone. What were those? Instrumental glitches, cosmic rays hitting the detector, or real astrophysical events? Neutron stars doing something, black holes doing something, mergers, jets, processes we do not have names for yet. The data is too sparse to say. But the possibility is there. Every time we improve our instruments, we find new things. Every time we build a faster survey, a more sensitive detector, a telescope that covers a wider field or samples more frequently, the universe shows us something we were missing. LF bots are just the latest example. In 10 years, there will be something else. Some new class of transient that makes LF bots look ordinary, and we will argue about what those are too. There is also the question of what happens between the extremes. We know supernovae happen, massive stars collapse. We know neutron star mergers happen. We detected one with gravitational waves. We know gamma-ray bursts happen, relativistic jets punching through stellar debris. Those are the bright, obvious events. But there is a continuum. Failed supernovae, where the core collapses but the explosion fizzles. The star dims instead of brightening. The core forms a black hole and just swallows the rest of the star. No bright transient, no jet, just a star that vanishes. We think this happens, the models predict it, but it is almost impossible to observe because by definition there is not much light. You would have to be monitoring a star at the exact moment it collapses and notice that it disappeared. A few candidates have been found, stars that were there in old images and gone in new ones. No supernova, no transient, just gone. Those might be failed supernovae, or the stars might have just dimmed below the detection threshold for other reasons. We do not know. And there are explosions that are not quite supernovae but not quite something else. Supernova imposters. Transients that look like supernovae at first but turn out to be massive eruptions from unstable stars. The star survives. It sheds a shell of material, brightens, fades, and then sits there, waiting to do it again a few years later. Eta Carinae is the most famous example. A massive star in our galaxy that erupted in the 1840s became one of the brightest stars in the sky for a few years, then faded. It is still there, still unstable, still shedding mass. It will probably explode as a supernova eventually, but not yet. How many other stars are doing that? How many transients that we classify as supernovae are actually imposters? And if they are imposters, what are they telling us about the final stages of massive star evolution? There are models, there are guesses, but the observations are incomplete. Neutron stars are involved in many of these edge cases because neutron stars are the remnants. If you want to understand how massive stars die, you have to understand what they leave behind. Some leave neutron stars, some leave black holes, some leave nothing we can detect, and the dividing line between those outcomes is fuzzy. The line depends on the mass of the core at the moment of collapse, it depends on the rotation rate, it depends on the magnetic field, it depends on whether the star is alone or in a binary system. It depends on the composition of the core, which depends on the star's mass and metallicity, and how it fused elements during its lifetime. There are a lot of variables. The models try to account for all of them, but models are only as good as the data we use to build them. And for rare events that happen once per galaxy per century, the data is thin. LF bots might be filling in one of those gaps. If they are real, if they are a distinct class and not just a grab bag of different events that happen to look similar, then they are telling us something about a specific channel of stellar death or compact object merger that we did not have a good handle on before. Maybe they are showing us what happens when a star collapses into a magnetar instead of a normal neutron star. Maybe they are showing us what happens when a neutron star and a black hole merge in a low-mass system. Maybe they are showing us what happens when a jet successfully breaks out of a supernova envelope and we happen to be looking along the jet axis. Any of those possibilities would add a piece to the puzzle, and the puzzle is large. Massive stars die in different ways. The more data we have, the more channels we discover. Supernovae, hypernovae, gamma-ray bursts, LF bots, failed supernovae, supernova imposters. Each one is a different path through the parameter space of stellar mass, rotation, metallicity, and environment. Each one tells us something about how stars work and what they leave behind. The challenge is that transient astronomy is young. We have only been systematically surveying the sky for transients for a couple of decades. Before that, we found them by accident. Now we find them on purpose. But even now, our surveys only cover a fraction of the sky, and they only sample at intervals of hours or days. There could be transients that last minutes. We would miss almost all of them. There could be transients that only happen once per million galaxies. We would need to survey millions of galaxies continuously to catch one. We are not there yet. The upcoming generation of survey telescopes will help. The Vera-C Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is designed to image the entire visible sky every few nights. It will find thousands of transients per night, maybe tens of thousands. The data rate will be overwhelming. Astronomers are already building machine learning pipelines to sift through the alerts, classify the events, prioritize follow-up. Because you cannot follow up on everything. There are not enough telescopes, not enough time. You have to choose. And choosing means you might miss something important, something rare, something that only happens once and never repeats. That is the gamble. The universe is big, events are rare, telescopes are expensive. You do your best and hope you get lucky, and luck matters. The cow was discovered by a survey. The follow-up observations were fast because the object was bright and obviously unusual. If it had been fainter, it might have been missed. If it had faded faster, the follow-up might have come too late. If it had been on the other side of the sky, hidden behind the sun, nobody would have seen it. Astronomy is full of near misses, transients that almost got observed but did not, signals that almost got detected but were just below the threshold, objects that were in the field of view but lost in the noise. Every detection is a combination of the event happening, the instrument being online, the weather being clear, the data pipeline catching the alert, and someone deciding to follow up. Remove any one of those, and the event goes unrecorded. We are mapping the universe one lucky break at a time, and the map is still mostly blank. LF bots are a reminder that the map is incomplete. We thought we understood the zoo of cosmic explosions. Supernovae over here, gamma-ray bursts over there, kilonovae in this corner. Then the cow showed up and did not fit any of those boxes. Now we have a new box, LF bots, and we are trying to figure out what goes in it and why. The process is slow, the data is sparse, the models are uncertain, but that is how science works. You find something that does not fit, you You try to explain it. You build models. You test predictions. You wait for more data. Eventually the picture clears up, or it does not, and you realize you are asking the wrong question. Either way, you learn something. What ELF-bots are teaching us, beyond the specific physics of jets and magnetars and mergers, is that the universe still has room to surprise us. Neutron stars, for all the decades we have spent studying them, are still doing things we did not predict. Mergers are messy, collapse is messy, jets are complicated, magnetic fields are complicated, and when you combine all of those ingredients in the extreme environment of a dying massive star or a colliding binary, the result can be something nobody saw coming. The cow was one example. There will be others. Each one will get a name. Each one will get a model. And each one will add another data point to the growing list of things neutron stars can do when they are pushed to the edge. So where does that leave us? We started this chapter talking about the cow, a bright, fast blue transient that peaked in 2 days and faded in weeks. We talked about how it did not fit the supernova template, and how the leading explanation involves a jet from a newly formed neutron star or a black hole. We talked about LF-bots as a class, a handful of similar events still not fully understood, possibly coming from multiple different processes that happen to look alike in optical light. We talked about jets and how they work and why they matter. We talked about the unseen phenomena, the transients we are probably missing because they happen too fast or too faint or in wavelengths we do not monitor. And we talked about the broader challenge of mapping the landscape of stellar death and compact object mergers with incomplete data and limited resources. The field is young, the sample size is small, the models are tentative, but the questions are clear. What makes an LF-bot? How common are they? What do they tell us about neutron stars and black holes, and the extreme physics that happens when those objects form or collide? And what else is out there, lurking just below our detection threshold, waiting for the next generation of instruments to bring it into view? Those questions are not abstract. They connect directly to the broader effort to understand neutron stars. Because neutron stars are not just objects, they are laboratories. Every observation, every detection, every weird transient that might involve a neutron star teaches us something about matter at densities we cannot replicate on Earth, about magnetic fields stronger than anything we can generate, about rotation rates that push the limits of what solid objects can sustain, about jets and shocks and particle acceleration in regimes we can only model. LF-bots are one piece of that puzzle, a small piece, but pieces add up. And the more we learn about what neutron stars can do, the more we learn about the universe itself, how it builds heavy elements, how it recycles matter, how it converts gravitational energy and rotational energy into light and particles, and the elements that eventually become planets and life. Neutron stars sit at the center of all of that. They are the engines, the forges, the remnants of stars that were once ordinary and became anything but. And LF-bots, strange as they are just the latest chapter in a story we are still learning to read. A story that started with a graduate student noticing a pulse in her data and wondering what it meant. A story that continues every time a survey telescope catches a flash of light where there was only darkness before. A story that will keep unfolding as long as we keep building better instruments, asking harder questions and paying attention when the universe decides to do something we did not expect. That is the frontier. That is where we are. And that is where we go next. We left off in the fog. Fast blue transients lighting up for a few days and then vanishing. Jets screaming out of collapsing stars or merging compact objects. Signals we barely understand, scattered across a universe that refuses to follow a script. LF-bots sitting in the data like questions we do not have answers for yet. And the whole time, while we were chasing those flashes and arguing about what powers them, neutron stars themselves were just sitting there. Thousands of them, spinning, glowing, waiting for us to catch up. Because as strange as the explosions are, as dramatic as the mergers and the gamma-ray bursts and the colonovae, the real story is quieter. The real story is what neutron stars are teaching us about the universe itself. Not just what happens when they die, what they are, what they contain, what laws of physics they obey or break, and what we still do not know. This is the last chapter, the one where we step back and look at the whole picture. Not the individual discoveries, not the specific events, the broader question. What are neutron stars actually for? And the answer, uncomfortable as it might sound, is that they are laboratories, not built by anyone, not designed. Just sitting out there in the darkness, operating in regimes of density and pressure and gravity that we cannot replicate anywhere else. They are natural experiments, the universe running tests on its own rules, and we are finally, after decades of building instruments and refining theories and arguing over data, in a position to read the results. Let's start with the simplest question. What is a neutron star made of? We have spent 7 chapters talking about density and spin and magnetic fields and collisions, but we have not definitively answered what is inside. And the reason we have not is because nobody knows. Not for sure. We have models. We have constraints from observations. We know roughly what the outer layers are. A crust made of neutron-rich nuclei arranged in a lattice, with free neutrons dripping out at depth. Below that, a fluid of neutrons with some protons and electrons mixed in. Possibly a superfluid. Possibly multiple phases of superfluidity at different depths. The models all agree on that much. But the core, the inner few kilometers where the density climbs to several times the density of an atomic nucleus, is still a mystery. And not a small mystery, a foundational one. Because at those densities we're no longer sure what matter is. Normal matter is made of protons, neutrons and electrons. Protons and neutrons are made of quarks. 3 quarks per proton, 3 per neutron. Up quarks and down quarks, held together by the strong nuclear force. The force is mediated by particles called gluons, and the whole framework, the theory that describes how quarks and gluons interact, is called quantum chromodynamics. QCD for short. The name is a historical accident. Quarks carry a property called color charge, not because it has anything to do with actual color, but because physicists needed a label, and color worked. QCD is one of the most successful theories in physics. It describes how protons and neutrons hold together, how atomic nuclei stay bound, how particles behave in high-energy collisions. The equations are solid. The predictions match experiments at particle accelerators to absurd levels of precision. But QCD has a problem. It is mathematically intractable at low energies and high densities. You cannot solve the equations exactly. You can run simulations, you can make approximations, but the regime inside a neutron star core, where the density is several times nuclear density and the temperature is relatively low by particle physics standards, is exactly the regime where QCD becomes impossible to calculate directly. The equations are too hard, the interactions are too complicated. Quarks and gluons are confined inside protons and neutrons under normal conditions, but at high enough density confinement might break down. The boundaries between protons and neutrons might dissolve. Quarks might move freely through the core, no longer bound into individual particles. Quark matter. A soup of up quarks, down quarks, and possibly strange quarks, sloshing around inside a sphere 20 kilometers across. If that exists, it is the only place in the universe where quark matter is stable. Particle accelerators can create quark-gluon plasma for fractions of a second by smashing heavy nuclei together at relativistic speeds, but the plasma expands and cools almost immediately. It does not sit there. Neutron star cores, if they contain quark matter, would be the only stable reservoirs of deconfined quarks anywhere. The only place you can study QCD in that regime is by observing neutron stars, not in a lab, not in a collider, out there, 10,000 light-years away, spinning, glowing, quietly running an experiment we could never afford to build. The problem is, we cannot see inside. We cannot crack one open. We cannot send a probe. Every piece of information we have about the interior is indirect. A shadow cast on the data. We measure the mass of a neutron star by watching how it affects the orbit of a companion star in a binary system. We measure the radius, sort of, by analysing the X-rays emitted from hotspots on the surface and modelling how gravity bends the light. We measure how the star deforms under tidal forces during a merger by analysing the gravitational wave signal. Each measurement gives us a constraint, a data point, a boundary in the parameter space of possible equations of state. The equation of state is the relationship between pressure and density for matter at nuclear densities. It tells you how stiff the matter is, how much it resists compression. Soft equations of state allow neutron stars to be small and easily compressed. Stiff equations of state make them larger and harder to squeeze. Different interior compositions produce different equations of state. If the core is pure neutrons, the equation of state looks one way. If it contains hyperons, particles with strange quarks, the equation of state softens. If it contains deconfined quark matter, it softens even more. Each possibility predicts a different mass-radius relationship. Measure enough neutron stars with enough precision, and you can rule out some of the models. That is the game. That is what the field has been doing for the last 2 decades, collecting measurements, tightening constraints, narrowing the range of possibilities, and the range is narrowing. The detection of gravitational waves from neutron star mergers, specifically GW170817, gave us the best constraint yet. The way the 2 neutron stars deformed during the final moments before they collided told us how stiff they were. The result ruled out the softest equations of state. Neutron stars are not as compressible as some models predicted. That eliminated a chunk of the parameter space. X-ray observations from NASA's Neutron Star Interior Composition Explorer, NICER, have added more constraints. NICER is an X-ray telescope mounted on the International Space Station, pointed at pulsars, measuring the arrival times and energies of X-ray photons with extraordinary precision. The X-rays come from hotspots on the neutron star's surface, and as the star rotates, the hotspots swing in and out of view. The way the light curve changes tells you about the star's shape, how much it bulges at the equator, how gravity bends the light as it escapes the surface. By modelling the light curve and the spectrum, you can infer the star's mass and radius. NICER has measured a handful of pulsars in detail, and the results consistently point toward equations of state that are moderately stiff. Not the stiffest models, not the softest, somewhere in the middle. That narrows the range further. It does not tell us definitively whether quark matter exists, but it tells us that if it does exist, it cannot be too soft. The core cannot collapse into a puddle. It has to have some structural integrity, some resistance. That is progress, small steps, but each step eliminates possibilities. The surprising thing, the thing that keeps tripping up the models, is how massive some neutron stars are. The heaviest confirmed neutron star, as of the last few years, weighs about 2.1 solar masses. Some candidates might be heavier. The uncertainty comes from measurement errors and the difficulty of confirming masses in certain types of binary systems. But 2 solar masses is well established. That is a problem for soft equations of state. If matter is too soft, if it compresses too easily under pressure, a neutron star that heavy should collapse into a black hole. The fact that it does not means the matter is stiff enough to hold up 2 solar masses. That rules out a lot of models with too many hyperons, models with early quark deconfinement, models where the core is mostly exotic particles instead of neutrons. All of those predict a maximum mass below 2 solar masses. The observations say otherwise, so those models are out. Or at least they need to be modified. Maybe hyperons do appear in the core, but only at higher densities than the models originally predicted. Maybe quark matter exists, but the transition happens gradually instead of abruptly, and the mixed phase provides enough stiffness to support higher masses. The details are still being worked out, but the constraints are real. Neutron stars are teaching us slowly and indirectly what matter does at densities we cannot reach any other way. Now let's talk about gravity. General relativity is the theory of gravity. It says that mass and energy curve space-time, and objects move along the straightest path through that curved space. The theory has been tested extensively in weak gravitational fields, the orbits of planets, the bending of light around the Sun, the precession of Mercury's orbit, gravitational time dilation near Earth's surface. All of those tests confirm the theory to high precision. But weak field tests are not enough. General relativity makes predictions about what happens in strong gravitational fields near black holes and neutron stars, and those predictions have only recently become testable. Neutron stars are strong field objects. The gravity at the surface is hundreds of billions of times stronger than Earth's. The escape velocity is a significant fraction of the speed of light. Time runs noticeably slower on the surface than far away. Light gets redshifted climbing out of the gravitational well. Space-time is curved enough that you can see distortions in the shape of the star as gravity bends the light rays. All of that is predicted by general relativity. And so far, every observation matches the predictions. Pulsar timing is one of the cleanest tests. Pulsars are extraordinarily precise clocks. By monitoring the arrival times of pulsars over years or decades, astronomers can measure tiny deviations caused by the pulsar's motion, its orbit, and the curvature of space-time around it. The Hulse-Taylor binary pulsar, PSRB 1913+16, was the first system where the orbital decay matched the predictions from gravitational wave emission to within a fraction of a percent. That was indirect evidence for gravitational waves, but it was also a test of general relativity in a strong field. The two neutron stars in that system are orbiting each other in a tight ellipse, moving at speeds where relativistic effects are significant. The orbit precesses. The timing of the pulses shifts as the pulsar moves toward and away from us. Every effect, every deviation matches the theory. No discrepancies. The double pulsar, PSRJ 0737-3039, is an even better laboratory. Both neutron stars in that system are pulsars. We can see pulses from both of them. The system is inclined almost edge-on to our line of sight, which means one pulsar occasionally passes behind the other, and the radio waves from the background pulsar get delayed by the curved spacetime around the foreground pulsar. That delay is called the Shapiro delay, and it is a direct test of general relativity. The amount of delay depends on the mass of the foreground pulsar and the curvature of spacetime around it. The measurement matches the prediction. Exactly. To within the measurement errors, which are tiny because pulsars are such good clocks. The double pulsar has been monitored for nearly 2 decades now, and every year the constraints get tighter. Every relativistic effect predicted by general relativity shows up in the data with the right amplitude and the right timing. Orbital precession, gravitational redshift, Shapiro delay, orbital decay due to gravitational wave emission. All of it fits, no deviations, no hints that the theory is breaking down. That is remarkable because general relativity is a classical theory. It does not include quantum mechanics. At some level, in some regime, the two theories have to merge. Quantum gravity, the theory that describes space-time at the smallest scales, where quantum effects become important. Nobody knows what that theory looks like. String theory is one candidate. Loop quantum gravity is another. There are others. All of them make predictions that differ slightly from general relativity in extreme conditions. Near the singularity inside a black hole, during the Big Bang, possibly in the cores of neutron stars if the density and curvature are high enough, but so far we have not seen any deviations. General relativity keeps working, even in the strong field, even in neutron stars where space-time is curved so sharply that light rays bend into spirals. The theory holds. That does not mean it will hold forever, it just means we have not pushed it hard enough yet. Neutron stars are one of the places where, if general relativity is going to break down, we might see it. Every new pulsar timing measurement, every new gravitational wave detection, every new mass and radius constraint, they are all tests, and so far Einstein is still winning. Now for something strange, neutron stars have planets. Not many. Not the kind of planets you would want to live on, but planets. The first confirmed exoplanets ever discovered, the first planets found outside our solar system, were not around a normal star. They were around a pulsar, PSRB 1257+12, a millisecond pulsar about 2,000 light-years away in the constellation Virgo. In 1992, astronomers Alexander Wolszczan and Dale Frail announced that they had detected periodic variations in the pulsar's timing that could only be explained by planets. 3 of them, orbiting the pulsar in a system that looked, in some ways, remarkably like the inner solar system. The planets were detected by their gravitational pull on the pulsar. As the planets orbit, they tug on the pulsar slightly, making it wobble. The wobble changes the distance between the pulsar and Earth by a few hundred kilometers over the course of each orbit. That is a tiny distance, negligible by human standards, but pulsar timing is so precise that a few hundred kilometers translates into a detectable shift in the arrival times of the pulses, a few microseconds. The timing variations were periodic, regular, and they matched the pattern you would expect from a multi-planet system. 2 of the planets are about 4 times the mass of Earth. The third is much smaller, roughly the mass of the Moon. They orbit at distances of about 0.2, 0.4, and 0.5 astronomical units, closer than Mercury orbits the Sun, and they are bathed in radiation. The pulsar is spinning 367 times per second, beaming high-energy particles and electromagnetic radiation into space. Anything orbiting that closes is getting blasted. These are not habitable planets. They're probably not even solid planets in the way we think of Earth. They are more like scorched remnants, dead worlds orbiting a dead star. The existence of pulsar planets was not predicted. It was a surprise, and the surprise raised immediate questions. How did they form? Normal planets form in the protoplanetary disk around a young star, gas and dust collapsing, clumping together, building up into rocky cores and gas giants. But pulsars are not young stars. They are the remnants of supernova explosions. The explosion should have destroyed any planets that existed before. The shockwave, the radiation, the sudden loss of most of the star's mass, all of that would unbind a planetary system. The planets would be flung into space or vaporized. So the planets around PSR B1257+12 must have formed after the supernova, somehow. The leading theory is that they formed from a debris disk, material left over from the explosion or from the disruption of a companion star. If the pulsar had a companion, and the companion was torn apart, either by the supernova or by tidal forces later, the debris would settle into a disk around the pulsar. The disk would cool, particles would collide, stick together, grow, eventually planets. A second-generation planetary system built from the ruins of the first, or from the ruins of a companion star that did not survive. Either way, the planets are ghosts, remnants of something that used to exist, now orbiting a corpse. The discovery of pulsar planets was a watershed moment for exoplanet science. Not because the planets themselves were interesting, they are not, they are irradiated hellscapes, but because the discovery proved that planets exist around other stars. Before 1992, that was still a hypothesis. We assumed other stars had planets. The math suggested they should, but we had no proof. The first detection could have come from a normal star. It did not. It came from a pulsar, a dead star. The universe has a sense of humour. The technique used to find the pulsar planets, measuring tiny variations in timing, became the foundation for one of the main methods of exoplanet detection. Radial velocity measurements. Watching a star wobble as a planet tugs on it. The wobble shows up as Doppler shifts in the star's spectrum. The same principle, applied to light instead of pulsar timing. Since 1992, astronomers have found thousands of exoplanets around normal stars. Hot Jupiters, super-Earths, ice giants, rocky worlds, some in the habitable zone where liquid water could exist. The field exploded, but it started with a pulsar and 3 dead planets nobody expected to find. A few other pulsar planets have been discovered since. Not many. Pulsars are rare. Pulsar planets are rarer. Most pulsars are alone. No planets, no companions, just spinning in the void. The ones that do have planets are curiosities, laboratories for studying planet formation in extreme environments. How do you build a planet in a radiation field strong enough to sterilize anything that moves? How do you keep a planet stable in orbit around an object that is spinning hundreds of times per second? What happens to the planet's atmosphere? Does it get stripped away? Does it glow in X-rays from the particle bombardment? We do not know. The observations are limited. The planets are small, far away, and orbiting objects that are themselves hard to study. But they are there, and they raise uncomfortable questions about how resilient planet formation is. If planets can form around pulsars, in the debris of a supernova, then planets can probably form almost anywhere. Debris disks, stellar collisions, the outskirts of galaxies where the gas is thin. Wherever there is material and time, planets happen. That changes the estimate for how common planets are, which changes the estimate for how common life might be, which brings us back to neutron stars teaching us things we did not expect to learn. Now let's talk about the future, because as much as we have learned from neutron stars over the last 60 years, we are still at the beginning. The detectors are getting better, the telescopes are getting sharper, the data rate is climbing, and the next decade is going to bring observations that were impossible a few years ago. LIGO and Virgo are being upgraded. The next observing run will be more sensitive by a factor of 2 or more. That means the volume of space they can survey goes up by a factor of 8. More neutron star mergers, more black hole mergers, more gravitational wave signals. Each one adds a data point. Each one refines the constraints on the equation of state. Japan's Kagura detector is coming online. India is building one. Eventually, there will be a global network of gravitational wave detectors, all running simultaneously, cross-checking signals, triangulating sources with much better precision than 2 or 3 detectors can achieve. Better localization means faster follow-up. Easier to point optical and X-ray telescopes at the right patch of sky in the first few minutes after the gravitational wave alert. Easier to catch the kilonova while it is still bright. Easier to measure the spectrum and learn what elements are being produced. NICER is still operating, still measuring pulsars, Each new pulsar adds to the dataset. Each new mass radius measurement tightens the constraints. There are plans for follow-on missions. Next-generation X-ray timing satellites with better sensitivity, better energy resolution, and the ability to observe fainter pulsars. X-ray polarimetry, measuring the polarization of X-rays from neutron stars, is a new frontier. Polarization tells you about the geometry of the magnetic field and the structure of the emitting region. XPE, the Imaging X-ray Polarimetry Explorer, launched in 2021, has started making polarization maps of pulsars and magnetars. The data is still preliminary, but the early results are surprising. The magnetic fields are more complicated than the simple dipole models predict. There are twists, asymmetries, structures we did not account for. More observations will clarify the picture, or make it more complicated. Either way, we learn. Radio telescopes are getting bigger and more sensitive. The Square Kilometre Array, SKA, is under construction. A network of radio dishes spread across South Africa and Australia, with a combined collecting area of 1 square kilometre. The name is literal. When it comes online in the late 2020s, it will be the most sensitive radio telescope ever built. SKA will find pulsars by the thousands, fast radio bursts by the dozens per day. It will monitor pulsar timing with precision high enough to detect gravitational waves at nanohertz frequencies from individual supermassive black hole binaries, not just the background. It will map the magnetic fields in pulsar wind nebulae. It will search for planets around pulsars. It will do things we have not thought of yet, because that is what happens when you build an instrument, an order of magnitude more sensitive than anything that came before. You find things you are not looking for, things that do not fit the models, things that force you to rewrite the textbooks. And in space, LISA is coming. The Laser Interferometer Space Antenna. 3 satellites flying in formation, separated by millions of kilometers, using lasers to measure the distance between them with absurd precision. LISA will detect gravitational waves at millihertz frequencies, waves from white dwarf binaries, intermediate mass black holes, stellar mass black holes spiraling into supermassive black holes, and possibly, if we get lucky, neutron star binaries in the early stages of inspiral, years or decades before they merge. LIGO catches the final moments, the last 100 seconds before the collision. LISA will catch the build-up, the long, slow spiral, watching the orbit decay over months or years, measuring the masses and spins with precision. LIGO cannot match, predicting when the merger will happen, alerting ground-based detectors so they are ready when the final plunge begins. Multi-messenger astronomy on a new level, coordinated observations across decades, following a binary system from the moment we first detect the gravitational waves, through the inspiral, through the merger, through the aftermath, watching the entire process unfold in real time. That is where the field is heading. The Vera C, Rubin Observatory, formerly the Large Synoptic Survey Telescope, is about to start operations. A ground-based optical telescope in Chile with an enormous field of view and a high-speed camera. It will image the entire visible sky every few nights, producing a continuous movie of the transient universe. Every supernova, every LF bot, every kilonova, every asteroid that moves, every variable star that flickers. The data rate will be overwhelming, millions of alerts per night. Machine learning pipelines are being built to sift through the alerts, classify the transients, and prioritize follow-up. Rubin will find neutron star mergers optically. It will catch the kilonova in the first few hours, before the light fades. It will measure the color evolution, the spectrum, the total energy output. Each observation will add to the library of kilonovae, refining the models of our process nucleosynthesis, improving the estimates for how much gold and platinum is scattered into space with each merger. And it will find things we did not predict. Transients that do not fit any known category, flashes that peak and fade in hours, signals that repeat on no schedule. Every time we build a faster survey, the universe shows us something new. Rubin will be the fastest survey yet. Beyond the instruments, there are theoretical frontiers. Simulations of neutron star mergers are getting more sophisticated. Higher resolution, better treatment of magnetic fields, better models of neutrino transport. Neutrinos carry energy away from the collision, and how much they carry matters. It affects the temperature of the debris. It affects how much material gets ejected. It affects the nucleosynthesis. Early simulations ignored neutrinos or treated them crudely. Modern simulations include them properly and the results are changing. The predicted kilonova light curves are different. The predicted element abundances are different. The predictions match observations better, but not perfectly. There are still discrepancies, still free parameters in the models, still assumptions that might be wrong. Each new observation constrains the models further. Each new simulation explores a different corner of the parameter space. The process is slow. Simulating a neutron star merger in full general relativity with magnetic fields and neutrino transport takes months of supercomputer time. You cannot just run 1,000 simulations to cover all the possibilities. You pick a few representative cases, run those, and interpolate. Then a new observation comes in and you realize the interpolation was wrong. You run new simulations, the cycle continues. There is also the question of what else we are missing. We have found pulsars, magnetars, fast radio bursts, LF bots, kilonovae. Each discovery came as a surprise. Each one required building new instruments or analyzing old data in new ways. What else is out there? What signals are we not detecting because we are not looking in the right wavelength, or the right timescale, or the right part of the sky? Neutron stars might emit gravitational waves continuously, if they are asymmetric. If the crust has a mountain a few millimeters tall, the star wobbles as it spins, and the wobble radiates gravitational waves. The signal would be faint, much fainter than a merger. But it would be continuous, always on. LIGO has searched for continuous gravitational waves from known pulsars and found nothing yet. The sensitivity is not high enough, but as the detectors improve, the searches will get deeper. If a neutron star is radiating gravitational waves continuously, we will eventually detect it, and that will teach us about the structure of the crust, how strong it is, how much deformation it can support before it cracks. There is the possibility of detecting neutrinos from nearby neutron stars, not from mergers, from isolated neutron stars that are still hot. Young neutron stars, a few thousand years old, are still cooling. They radiate neutrinos from the core as the thermal energy leaks out. The neutrino flux is tiny. Detecting it would require a neutrino telescope with a huge volume and incredible sensitivity. IceCube, the neutrino detector at the South Pole, is sensitive to high-energy neutrinos from astrophysical sources like supernovae and active galactic nuclei. But it is not sensitive enough to detect the low-energy neutrinos from a cooling neutron star. Future detectors might be. If we could detect those neutrinos, we would learn about the cooling rate. How fast the core loses energy, that depends on the composition. Superfluid neutrons cool faster than normal neutrons. Quark matter cools at a different rate. Neutrino detections would be a direct probe of the interior, not indirect, not inferred from mass and radius, direct. The neutrinos are coming from the core. Measure them and you know what is inside. That is a long way off, maybe decades, but it is possible. And then there is the question of what neutron stars teach us about the universe at large, about how matter behaves, about how the elements are made, about how gravity works, about how stars live and die. Every neutron star observation feeds into a larger picture. The cosmic chemical evolution, the distribution of elements in the galaxy, the rate of supernova explosions over the history of the universe, the population of compact objects. How many neutron stars are there? How many black holes? How often do they merge? How much energy do they release? How much do they contribute to the gravitational wave background? These are not abstract questions. They connect to the history of the galaxy, to the conditions that allowed the solar system to form, to the availability of heavy elements needed for rocky planets and eventually for life. Every atom heavier than hydrogen in your body was made inside a star or in a supernova or in a neutron star merger. The iron in your blood came from a supernova. The gold in a ring came from a neutron star collision. You're made of stellar debris. Neutron stars are part of that story. They are the forges, the recycling plants, the engines that turn hydrogen and helium into everything else. The broader implication is that neutron stars are not just strange objects to catalogue and study. They are essential to the cosmic ecosystem, essential to understanding how the universe builds complexity, how it goes from a hot uniform soup of hydrogen and helium after the Big Bang to galaxies and stars and planets, and eventually to chemistry and life. Neutron stars sit at a critical point in that chain. They are the remnants of massive stars, the stars that produce the heavy elements, The stars that explode as supernovae and scatter those elements into space. The stars that, when they collide as neutron stars, produce even heavier elements that cannot be made any other way. Without neutron stars, the periodic table stops at iron. Without neutron stars, there is no gold, no platinum, no uranium. Without neutron stars, rocky planets are less common because you need heavy elements to build them. And without rocky planets, life as we know it does not get started. That is the connection. That is why neutron stars matter. Not because they are exotic, because they are necessary. So where does that leave us? We started this video talking about density. 10 quadrillion kilograms per cubic centimetre. A teaspoon weighing 1 billion tons. Numbers so absurd they sound made up. We talked about how neutron stars form. Massive stars collapsing. The core compressing down to city size. The outer layers exploding into space. We talked about the surface, the gravity, the heat, the impossibility of standing on something that would flatten you into a layer a few atoms thick. We talked about the interior, the layers, the crust, the superfluid core, the uncertainty about what sits at the very centre, neutrons, quarks, something else. We talked about pulsars, lighthouse beams sweeping across the galaxy, millisecond pulsars spinning hundreds of times per second, magnetars with magnetic fields strong enough to warp atoms. We talked about the signals, fast radio bursts, the 22-minute pulsar, antimatter streaming off pulsar wind nebulae. We talked about gravitational waves, the first detection of a neutron star merger, the kilonova, the heavy elements scattered into space, the confirmation that short gamma-ray bursts come from mergers, the constraints on the equation of state. We talked about LF bots, bright, fast, blue transients that do not fit the models, jets from newborn neutron stars or mergers or something else entirely. And we talked about what comes next. Better detectors, more observations, tighter constraints, new discoveries. Neutron stars are not finished teaching us. They are sitting out there, spinning, glowing, occasionally colliding, and every time we point a new instrument at them, we learn something about matter, about gravity, about the universe. They are natural laboratories, experiments we could never afford to build, conditions we could never replicate on Earth, densities 10 to the 17 times higher than water, magnetic fields a quadrillion Gauss, rotation rates that push objects to the edge of flying apart, collisions that release more energy than entire galaxies, all of it happening right now, at this moment. Thousands of neutron stars in the Milky Way alone, each one a data point, each one a test of the laws of physics, and we are just beginning to listen. The phrase that keeps showing up in the literature, the one that captures the uncertainty and the excitement, is that the neutron star core is the well-kept secret of neutron stars. We know they exist, we know roughly what they do, but the fine details, the stuff at the very centre, where the density is highest and the pressure is most extreme, remain hidden. Not because we are not trying, because the universe does not make it easy. You cannot see inside, you cannot touch it. You can only infer, measure the mass, measure the radius, measure how the star deforms under tidal forces, measure the gravitational wave signal, measure the neutrino flux if you get lucky. Each measurement adds a piece to the puzzle. Slowly, the picture is coming into focus. We know more now than we did 10 years ago. We will know more 10 years from now, but the core, the secret, is still locked away. Inside a sphere of neutron-degenerate matter, compressed to the point where atomic nuclei dissolve, held together by forces we can barely calculate, sitting at the edge of what matter can be before it stops being matter and becomes something else. Neutron stars have been called gigantic nuclei. That phrase, from older references, captures something important. They are not stars in the way we normally think of stars. They are not burning fuel. They are not fusing elements. They are not generating energy through chemistry or nuclear reactions. They are just sitting there, held up by quantum mechanics, neutron degeneracy pressure, the Pauli exclusion principle applied to neutrons instead of electrons, the same principle that keeps white dwarfs from collapsing, applied one level deeper. And that principle, that quantum mechanical rule that says you cannot put two identical fermions in the same state, is the only thing standing between a neutron star and total gravitational collapse. Remove that rule and the star becomes a black hole. Instantly. Quantum mechanics is not optional. It is structural. It is load-bearing. And neutron stars are the proof that quantum mechanics works even when the object is 20 kilometers across and weighs more than the Sun. The quantum world and the cosmic world are not separate. They are the same world, just different scales. Neutron stars sit at the intersection, large enough to see across the galaxy, small enough that quantum effects dominate the structure. They are bridges between the world of particles and the world of stars, between theory and observation, between what we can calculate and what we can measure. The future of neutron star research is not just about building better instruments or running more simulations. It is about closing the gap between what we predict and what we observe. Every time that gap narrows, we learn something fundamental about QCD, about general relativity, about the limits of matter, about how the universe works when you push it to extremes. Neutron stars are the extremes. They are what happens when gravity wins almost everything, but not quite. When matter compresses until it cannot compress anymore. When magnetic fields grow so strong they affect the vacuum. When rotation speeds up until the surface is moving at a quarter the speed of light. When two of them collide and briefly become the brightest thing in the universe. That is not an exaggeration. For a fraction of a second, a neutron star merger outshines everything else. Not in visible light, in gravitational waves, in space-time itself. The ripples carry more energy than all. So here we are, standing at the edge of what we know, staring at objects that refuse to behave the way comfortable physics says they should. 10 quadrillion kilograms per cubic centimetre. A teaspoon that weighs 1 billion tons. Numbers so violent they sound fictional until you remember they are not predictions. They are measurements. Neutron stars are real. They're out there right now, spinning hundreds of times per second, glowing in X-rays, occasionally tearing each other apart and scattering gold into the void. And every atom of that gold, every heavy element in your body, in the ground, in the device you are holding, came from events like that. You are not separate from this. You are made of it. We have spent centuries building instruments to see farther, measure smaller, think harder. And every time we do, the universe shows us something we were not ready for. Pulsars that tick like clocks, magnetars that crack their own crusts, mergers that ring space-time like a bell, fast blue transients that flare up and vanish before we can figure out what they are. The list keeps growing. The models keep failing. And that is not a failure of science. That is the process. You find something strange. You try to explain it. The explanation does not quite fit. You refine it. You wait for more data. You build better tools. Slowly the picture clears, or it does not, and you realize you are asking the wrong question. Neutron stars are not the end of the story. They are not even the strangest thing out there. But they are the edge. The place where matter stops being matter the way we understand it and becomes something else. Something we can observe but not touch. Something we can model but not fully explain. And they are still teaching us. Right now, every pulse, every flare, every collision. The universe running experiments we could never afford, and we are finally learning to read the results. So listen for the next pulse, flare and chirp. Because the smallest stars may still hold the largest unanswered questions,